Okay, so first a quick announcement. So the lightning talks are going to start at noon today, so in an hour. Everyone who submitted a lightning proposal is approved, so all of you are going to be called up to present. You can still submit lightning talks if you want. Really, if you have like job announcements, or if you're doing any sort of interesting, if you have an interesting project you'd like to tell folks about, you're very welcome to present. And like I said, everybody who submitted will have 2 to 3 minutes to come on stage and tell us what you do. So looking forward to that session. Okay, so with that, let's get started with the second session of today. So our first speaker is Yehuda Lindell, who's going to tell us about threshold signatures. Yehuda has been working in crypto for over 25 years. He is a professor at Bar-Ilan University. At some point, I guess being a professor was not challenging enough, so Yehuda set up a startup company doing multi-party computation. The company was acquired recently by Coinbase, and now Yehuda is the head of the crypto group at Coinbase. So Yehuda, I'm looking forward to your talk, and the floor is yours.
Thank you very much, Dan. It's both an honor and a pleasure to be here. So I'm going to talk about conservative cryptographic design. It's not the political use of the word conservative. I'll explain in a moment. So the thesis that I want to present is that the way that we do cryptographic design, maybe in academia or for the purpose of advancing science, is actually dangerous in today's environment. And I mean that very, very literally, and I'll explain why. So this is an incredible space. If we think about generally the time that it takes to transition something from a scientific result to use in practice, it's typically counted in maybe not decades, but many, many, many years. Here we can publish a paper, and 6 months later, a year later, or even before it's actually published, it can already be on the way to deployment. That makes it extremely exciting, adventurous, and very, very unique. The problem is that we're actually doing something that has a lot of significance financially for many, many people. And just to be very, very concrete, as we see this field growing, and as we want more and more people to be involved in this field, it's people's retirement funds that we're protecting, it's their children's college funds that we're protecting. It's not fun and games. It's not, without belittling credit card numbers or PII, it's not losing that. It's losing something which could have a lot of ramification. And the problem starts with a number of misunderstandings. Firstly, some or many practitioners think that a published paper has been verified. And in fact, this morning I was talking to a colleague and someone who knows the cryptography world well, and she asked me what I'm going to speak about, and I told her, and she said, I'm blown away. I was sure that if something has been published in a conference, that means that it's undergone rigorous review in terms of the validity of the results. And that's just not the case. And in fact, even some practitioners will see something on arXiv and say, okay, it's a published paper, it's the written word, it has theorem followed by proof, it must be okay, let's run and deploy. We can laugh, but it's actually very true as well. So we can take it with some humor. Academics have a certain way of speaking. There are some nuances to our disclaimers, things like we can prove this under an ad hoc assumption that sounds reasonable is something that anyone with academic training will say, not ready for deployment, needs to be studied for many years. But many practitioners will read this and say, okay, sounds reasonable. These are 2 or 3 extremely distinguished professors. If they say it sounds reasonable, it must be all is good, let's run and deploy. And on the other side, many or some academics don't appreciate the ramifications of a slight typo in a paper, because often those typos or underspecified protocols actually have no ramification on the scientific result. The scientific result is valid, everything, all is good. So I didn't say that you have to check that a point is on the curve. I didn't say that you have to check that the size of the modulus is beyond this. It doesn't make a difference. The result is still correct. But when you deploy, it now can be completely broken. And these things make it very dangerous. So what I want to argue is that we should be promoting more conservative protocol design and being more careful, wary, and cautious. So what do I mean by conservative cryptographic design? First, minimal assumptions as much as possible, and explain in the talk what I mean by that. Simple proofs and non-novel cryptography is great, It's the best. I mean, if it's simple and it uses stuff that is 20-year-old cryptography, 25-year-old cryptography, before I had gray hair, then that's also great. Clarity around trade-offs. If we are trading things off, efficiency versus assumptions and other things, let's make that very explicit. We don't always need the highest efficiency. If it takes 2 milliseconds or 20 milliseconds to generate an ECDSA signature that we're putting on Bitcoin or Ethereum, it actually is unlikely to make any difference for the vast, vast majority of applications. So yeah, we don't want to pay for nothing. If there's no point, we're not going to add in loops which don't do anything, but we don't need to always push for the highest efficiency. And also robust security definitions that I call that aren't brittle. What I mean by that is that if we slightly change something in the world, our security proof still stands, and I'll explain what I mean by that later on as well. So, and what is aggressive protocol design? Aggressive, in at least here being the antonym of conservative, pushing the limits of efficiency, heuristic arguments, new, less well understood techniques and assumptions, things that scientifically make a lot of sense. Science is about pushing the limits, advancing the scientific knowledge, but doesn't always coincide with what we want when we're actually deploying in practice. And just to make it very clear what I mean by conservative versus non-conservative, careful, cautious, circumspect, considerate, safe, wary, heedful, versus bold, brash, impetuous, rash, even reckless. This is exactly what I'm talking about in this space. Okay, so this talk is going to contain some criticism. It's constructive criticism, but that's always a bit dangerous. There's a sort of a fine line between criticizing for the purpose of a productive, constructive, academic, and professional discussion, and trashing other people. So please understand that this is a professional discussion. It's a discussion which is here to advance the field. There's nothing personal. There's never any criticism of mistakes. I've made so many mistakes in my career that I have no right to criticize anybody for making mistakes. It's not mistakes. It's about a direction that I think we should be going, and that's the discussion that I want to have. Okay, so let's start with efficiency. It's really hard to publish a paper that's less efficient than others. If you write in the abstract, we have a new protocol for Schnorr threshold signatures, which is 20 times slower than the previous best. That doesn't go across well with reviewers. And therefore, what we actually always have to do is be more efficient in at least some parameters, or there has to be something very clear that we're much better than the previous work. We have to be aggressive because previous work under maybe less well understood assumptions still has the title of being something which is much, much faster. So this pushes us to do some things which are very, very problematic. So I've semi-anonymized all the papers that I'm bringing here. I've removed the list of authors. You can, just so that at least it's not, up there. But here's a paper that does threshold ECDSA. And the paper uses, in order to prove security, uses a range proof on what's encrypted inside Payer. The details aren't important. But the authors say we conjecture that these zero-knowledge proofs are not needed because the leakage is so small that everything is fine. And to support our conjecture at the bottom here, we rely on an ad hoc assumption. Again, the nuances of academic speak. This paper, without the proofs, was deployed, implemented, in practice, and the results are very, very unfortunate because without those range proofs, the entire security of the protocol completely crashes. And in fact, with the 8 signatures only, you can extract the entire secret key. Right, this is devastating. Again, a library that was in production. And although the authors did put those caveats, ad hoc assumption, all of the times, the efficiency, the primary result was without those zero-knowledge proofs. So a practitioner reading this paper is going to understand that these are, again, well-established researchers, professors. We can trust them, yet the result is very, very problematic because there's this drive to always be much, much more efficient. With those range proofs, it wasn't nearly as efficient, and that would have been a problem in terms of publishing. But the result, when we're looking at publishing in a field where we're implementing today, it's very, very problematic. Concurrent composition. Basic definitions for MPC, for multi-party computation, or for threshold signatures considers the standalone setting. Well, standalone setting means I'm just running the protocol in isolation as if the rest of the world doesn't exist. That actually implies security if I run the protocol sequentially, which in some cases in this space actually it can be enough. But in many cases, we are considering a more general setting where there's concurrent protocols running with the same key, with related keys, with other things. And do we care about this, or should we care? I mean, it's a theoretical problem, maybe. We don't necessarily know of attacks. And here's a quote that I saw actually in a library in some company, which I'm not going to mention, that the software engineer wrote, I don't know why we need this. I suspect it's some abstract nonsense necessary for the proof to go through. So a lack of respect of, you know, if we can't prove it, I don't know if it's secure. I have no way of establishing security without proving. Sometimes I need to add things to the protocol to prove, and I can actually, a decade later, realize why I need it. And I have an example of that of one of my works in 2007. We had to change something in the protocol. No idea why. We couldn't see any attack. A decade later, someone published another paper about something else that showed had we left the original protocol the way it was originally before we did the proof, it actually would have been broken. Fortunately, we didn't do that. So there's a problem called ROS, not that important, but it was basically an assumption used to establish concurrent security for blind signatures, threshold signatures. And this was an assumption around for a couple of decades. So it's a well-established assumption. We've known about it for many years. However, the question is how many people looked at it. It was completely broken in polynomial time or sub-exponential time, depending on the parameters, but it doesn't matter. And breaking blind signature schemes or threshold signatures like GJKR, the original version of Frost, some multi-signature schemes. Some of these schemes had no proofs. How in 2020 we're publishing papers and promoting signature schemes that have no proofs, I have no idea. But some of these actually have proofs of security. But they're proofs of security for this sequential composition model and not for the concurrent security model. And it turns out they become completely broken in that setting. So again, looking at these more stringent definitions, even if we don't know of any attacks, can be the prudent thing when we're dealing with very large sums of money. Assumptions and definitions. What assumptions do I make? What definitions am I using? What model am I proving security in, and do I care? For assumptions, there are many possibilities. One's minimal assumptions. It means I prove my threshold protocol secure under the assumption that the signature scheme is secure. If Schnorr is secure, then my threshold signing protocol is secure. I don't need anything else. That's fantastic. It also means it's never my problem. You chose to use ECDSA on the blockchain, not me. If it's broken, it's your problem, not my problem. My threshold signing protocol is just as secure. That's fantastic. At least you can't blame me. But sometimes we can't do that, so we add standard assumptions, and we try to minimize them. And sometimes we add non-standard known assumptions, like maybe one more discrete logarithm, which I'll come back to. Or sometimes new ad hoc assumptions that I'm making up, and sometimes just pure heuristics. With models, I have the standard model proof where I just prove a reduction. I can use the random oracle model or a generic group model. I don't want to go into too many details. I'll just say very briefly the random oracle model is one that personally I'm comfortable with. Hash functions are constructed to behave somewhat in this manner. The generic group model is a model I'm very uncomfortable with. Elliptic curve points in the generic group model have no structure, but in the real world they have a lot of structure. They are actually a pair of numbers. Elliptic curves are not constructed to be random looking, and therefore I'm very suspect of this model. It doesn't mean it can't be used, but the question is what it does for you. If you want to use it as a way to explain why we haven't been able to get more, better than square root size of the group discrete log algorithms for elliptic curves, it's great. If you want to explain why ECDSA hasn't been broken, maybe it's great. But the reason why I think ECDSA is secure is because it's been around for 30 plus years and no one has broken it. Not at all because we have this generic group model proofs, at least that's my subjective opinion. So, but we come across these things. Here's a paper doing two-party threshold ECDSA, claiming from ECDSA assumptions, but in fact, it doesn't reduce to ECDSA. It reduces to some very, very complex functionality on the right-hand side. There's this very complex game that you can prove secure in the generic group model, but generic group models for ECDSA are really bad because in ECDSA you're mapping an actual number which is part of a point to a scalar in another group. So it's really not a very good match, and this is not a conservative design. It's aggressive design. They have these more complex definitions so they can get 2 rounds, but there's a price to pay for it. Frost is a protocol that has made a lot of noise. I want to talk about Frost because of the trade-offs. I want to stress it's not a criticism of the Frost protocol itself. It's not a criticism of the scientific process around Frost, which is introduce something, prove it under a less good assumption maybe, improve that over time, reduce the assumptions. We've seen this many times with many things in our field. But it is a criticism of the rush to standardize and to encourage people to deploy something which is very premature in terms of our understanding of its security. So what is Frost? It's a multi-party Schnorr signing protocol. The first version was completely broken by ROS. Okay, so it was fixed. The fixed version had a proof, but the proof was actually not for the protocol itself. It was for a protocol where it was a verifiable random function was used instead of a random oracle, and these are 2 very, very different beasts. Again, maybe it's a process, but this isn't clear, and people are already starting to be encouraged to deploy. The good news is in Crypto 2022, 2 weeks ago, 2 papers were published that prove Frost under the one more discrete logarithm assumption, which I'll talk about a bit more later, and the random oracle model, but the key generation in Frost still requires a generic group model in order to prove. Okay, but here's the concern. The proofs are still very fresh, hot off the press, and as I said, the fact that it's published in Crypto doesn't mean that we have a high level of confidence in the proofs yet, although I just want to stress, these are really good researchers who wrote the proofs, so, I'm saying they're suspect. It's a complex proof using forking lemmas, it's not a trivial proof that we can just immediately say yes. But much more importantly, standardization began in February 2021, a year and a half before we had a proof. And people were encouraged to go ahead and implement this and to use it now, a year and a half ago. But there was no proof. That, when we're talking about holding and protecting people's money, concerns me very, very significantly. And also in general for the field, if we want people to have confidence in cryptocurrency, we need to make sure that their funds, that their money is safe. And if we're reckless, if we use the philosophy of, if you're not breaking it, then you're not going fast enough. If we have that philosophy when protecting people's money, then people can't have trust in what we're doing. So I think that we just cannot afford to work in this way. And personally, I would be much, much too scared. At Coinbase, we have hundreds of billions of dollars at stake. This is a big deal. We take it very, very seriously, and we want to be very, very conservative in what we're doing to make sure that anybody who's using our schemes in this field is going to be safe. The design principles for Frost were strongly driven around a couple of things. Firstly, the requirement of having only 2 rounds, not 3 rounds. And maybe there are some people who say, well, if I have a cold element involved in the MPC, I need to take a message and walk into another room and connect something and then take it back and come back again. I understand. I think there's a very qualitative difference between 1 round and many rounds because of that. I'm not sure there's a big difference between 2 rounds and 3 rounds, but even if we accept that some people need 2 rounds, or many people want 2 rounds, and it's not the same always want and need, as I always tell my kids. It's not always the same, but the fact is that many people don't need it, and there isn't an option. It's not like we're saying, okay, here's a 3-round option, and here's a 2-round if you really need it, but understand that there's a price. Also, really high sufficiency, no zero-knowledge proofs, but the cost of these zero-knowledge proofs is milliseconds or even sub-milliseconds, and communication will anyway almost always dominate, so I just don't think it's really a big deal. And there are major trade-offs that we make in order to achieve this highest efficiency, and no one's talking about them, so I will. It has a proof using the one more discrete logarithm assumption. This is a well-known assumption for many years, but then again, so was ROS. It's not falsifiable, which means it's, as an assumption, you can't build up an experiment like publish the RSA challenge. You can't publish the one more discrete logarithm assumption challenge. And also, so it's a far less standard assumption. It's an interactive assumption. It's not falsifiable. And again, it has a proof, but it's really hot off the presses proof. How much confidence do we have in it? I have a lot of confidence in the people writing the proof, but do we have enough confidence to be deploying already now? That's a question that we have to ask ourselves. The proof, in terms of the model for the proof, the definitions are, there are two main models. One is a simulation-based definition, and one is a game-based definition. And both are very well accepted, and both have advantages. A simulation-based definition basically means that I'm telling you the protocol works in the same way as if you computed locally in a secure environment. Okay, that's basically what I'm saying. So you can think about that this threshold protocol with parties interacting and sending messages behaves just like this trusted third party, this secure environment that will compute it locally. Okay, so if local computation is fine, then this is also fine. And this holds actually for all inputs. So even if you have, for example, related keys, which I'll come back to in a moment. In a game-based definition, the definition is very tailored for the specific protocol and setting, and you have a game where parties interact, and then you reduce that if you can break this threshold game, then you can break some assumption like one more discrete log. So Frost is game-based, proven for this OMDL. Now let's talk about something that many people do. They do some type of Bip derivation. And when you do Bip derivation, so there's hardened derivation and normal derivation. Hardened derivation gives you pseudo-random keys. They look independent. Everything should be okay there. Should be. But normal derivation gives you related keys. If you're using a simulation-based proof, then I can tell you that as long as this Bip derivation is secure when you compute locally, then my proof of security for my threshold scheme goes through. This is that brittle definitions that those brittle definitions I was talking about. In a simulation-based definition, at least with universal composability, it's not brittle. If you generate the keys in a non-random way, and you can claim that that's secure when you're doing local computation, then my threshold protocol is untouched. It's all is fine. But if you use a game-based definition, you have to reprove your security, because your reduction most likely won't go through. At least the definitions certainly don't guarantee it, and in practice, most proofs won't actually go through. And if someone now comes up with a different type of derivation, they change the derivation protocol in some way, you have to go back and reprove your threshold proof again. So this is the more conservative approach, is to be simulation-based and less brittle. Now, sometimes I really need 2 rounds. I have to have it, and that's the requirement. Fine, you're allowed to make that choice. Every organization, every person running an organization makes their own trade-offs and make their own choices, but we have to make it very clear to them what the price is that they're paying. What are they losing by making that choice? And then they can make a decision. How much is at risk? Is it a few $100,000 or is it $10 billion? Is it, are they, do they want to be a more conservative, trusted organization or a faster, I don't know what organization, but everyone can make their own choice, but let's be very clear about what they are. I'll finish by just mentioning that it's possible to do Schnorr very, very easily in 3 rounds. It can be easily constructed and proven secure with perfect security in a random oracle model. That might sound a bit strange, but it's true because you're reducing to Schnorr. It's a simulation-based definition. It's probably too trivial to publish because it's just not difficult. It's the protocol that I would expect a grad student to come up with in a graduate course. And when reviewers say, so what was hard in the proof, the answer is nothing, and they generally don't like it. But that also means it's really easy to verify. If you read the proof, it's just really easy the addition of the zero-knowledge proofs, the additional round just makes everything very, very clean and simple. I mean, Schnorr is easy, it's linear, it should be easy, and with this protocol, it is easy. It's still really, really fast. I'm sure that the latency on the communication is still going to dominate. And if you're interested, you can have a look at it on ePrint. And if you don't need something which is overly aggressive, this is, in at least my subjective personal opinion, a much more conservative design. So to sum up, when it's absolutely necessary, yes, Being aggressive maybe is needed. As science, to advance science, we should certainly be aggressive because that's part of what we need to do. But we need to be very, very clear, and we are in a field where people are actually going and deploying things we publish now, and for that we need to be much, much more conservative. Especially in blockchain, really, really really, really low latency for signing is not something that is necessary for most applications, at least to what I understand. And let's be very clear that there's a price for aggressive design. There's a lot we gain by conservative design, and I personally very much advocate for conservative. Thank you very much.
Okay, great. We have time for some questions. Thank you, Yehuda. I'm going to take my prerogative as a session chair and ask a question myself. So I am almost afraid to ask this, but I am very curious what your thoughts are on the world of snarks, where there we know that we are required to use non-falsifiable assumptions. So there we have to go to kind of harder assumptions.
So again, when you don't have a choice, it already becomes a very, very different. But I would argue that this is, if we're using it for roll-ups of smaller amounts, and I'm assuming that's what we're doing, then this is the trade-off that makes sense. If I'm going to do a massive transaction, maybe I shouldn't do that in a roll-up. I should do it directly on the blockchain and pay the transaction fee because it's a massive transaction. When I'm doing a roll-up of a lot of small transactions, maybe it's, it's okay, but...
Okay, sounds good. Yeah, looks like we have a lot of questions for you.
Yoda, God bless you. God bless your talk. We need sanity in our space. I thank you. I hope more cryptographers are inspired by your message. What can we do as a community to stop this kind of peacocking that we like to do as cryptographers? 3 rounds versus 2 rounds, 100 milliseconds to 20 milliseconds. Should we start a high assurance cryptography conference? What should we do?
Wait, there is a high assurance cryptography conference.
Great.
I think it's a matter of really understanding what the real needs are when we do practice, and be very careful of practitioners or cryptographers who are involved in practice who have one experience and explain that this is what everybody needs. So to understand that there are many, many different scenarios. Sometimes we need one thing, but in many other places we need other things, and we just have to accept and understand. And if we're doing applied research, we should be aware of that and make sure that we talk specifically to, or we explain where we're working to. I can't solve the problems of program committees that don't want something which is more efficient, and we'll see that there is a protocol 2 years ago that was more efficient, and even though the proof was never fully published, and there is no full version on anywhere, and so on and so forth, it's just awareness. I guess speaking like this and promoting these sort of conversations maybe can help.
Thank you.
Let's take a question from the other side.
Hi, thanks for the talk. I wanted to ask you about deployment architecture. Right now we have test nets, and then it moves on to main nets. Do you see this as but then nobody really hacks the test net, and you might have another scenario where you start deploying on lower TVL blockchains, but then those blockchains will just get worse and worse because they're the ones that are hacked the most. How do you see kind of the deployment infrastructure moving forward to make it more secure?
My opinion is that any break to any hack to any organization is bad for the field. So if you're deploying, you say if it's a testnet is you're playing around. But if even if I have a smaller blockchain now and the amount of funds there is low, so maybe it's okay, I'm only protecting a small amount of funds, it's okay to be more aggressive. Think of what happens if you succeed. If you succeed, suddenly now protecting a large amount of funds there. Now you're going to go and roll back to something which is slower, doesn't scale as well. You're not going to do that. So I think you have to build in security from day one, something that's conservative, rather than being too, again, it's always a trade-off, and every organization has to make their own choice. For me, I honestly believe that, as an employee of Coinbase, I think it's bad also for Coinbase if some other organization is hacked. I don't want to see anyone hacked because it lowers our trust in this field. We want everybody to join. I don't want anybody to be broken. So if you're asking me, I'd prefer that you always do something conservative. But you can't. There are always going to be organizations that are more conservative and less conservative, and there's nothing we can do about that.
Okay, think we have time for one more question. So
Okay, and thank you so much for the talk. I found it very inspiring. One thing that I'm concerned about, and I don't have a particular question, but I wanted to share it with you and the audience, is that, I'm a bit concerned at how much these like foolproofs that we make for protocols that we do are being reviewed by reviewers. A lot of reviewers are also in rush, like accept a paper, as you said correctly, that based on the efficiency improvements, but we don't really spend time to check whether the proof was correct and properly. So we had like protocols like, for example, BGW in 1988, that we had a sketch of the proof for like 23 years until you and Gilad proved, the full security of the protocol. So should we rely on these sketches of the proof so that at least the reviewers, crypto reviewers can verify quickly without, like, even if they don't have time to spend like for reading 20, 30 pages of proofs? I mean, what should we do? What do you suggest?
So when we're deploying, I think we have to be very, very careful. I can tell you what we do. What we do when we're actually deploying. Firstly, we don't trust any paper. Any published paper, we will independently review and verify the proof. And if we've written the proof, then we have an independent person on our cryptography team review it, and there's a security team that runs an independent review as well, using either cryptographer in-house or external consultant. So that's the first stage. Then after that, we write a spec, because a protocol in a paper is not a spec. It's very underspecified. And we have an independent review that the spec matches that theoretical paper. And we do that in the cryptography team, and we do it independently in the security team. And then the engineering team writes the code. I don't write code. Never. So they write the code, and then we independently, in the crypto team, will review that the code matches the spec, and the security team will review that the code matches the spec. Is it perfect? No, but that's the type of due diligence that I think we need to carry out when we're deploying something that protects something so much that's so valuable.
Thank you.
Not to mention that there are auditing firms that specialize in verifying.
Yeah, on top of that, we do that as well. Yeah, of course, yes. Absolutely.
Fantastic. All right. Thank you, Yehuda. Thank you so much. Okay, our next speaker is Vitalik Buterin, the father of us all, the reason why we're all here. And so, Vitalik, really looking forward to your talk.
Thank you. Great. So, responding to 51% attacks, right? 51% attacks are, I think, basically the only serious threat to a blockchain functioning from a technical level, right? In the sense that, their blockchains run on many kinds of assumptions. There's cryptographic assumptions, but those cryptographic assumptions are fairly robust. The entire internet often runs on different assumptions that are basically the same as what blockchains use. But the thing that makes blockchains different from other kinds of cryptography is like this reliance on consensus, right? This idea that you have like a bunch of different nodes and you're relying on more than half of those nodes to be honest. And being honest really means lots of different things, right? It basically means that you are building blocks on top of other blocks that are the head of the chain. It means that you're attesting to the correct blocks. It means that you're not pretending that certain other blocks don't exist. There's a lot of different rules that miners or validators or any node that's running a blockchain has to follow. And you're really relying on this assumption that the majority of them actually do this, right? Now, it seems like a kind of fairly trivial assumption, right? Who here in this room is honest? Raise your hand. Who here is honest? Who here is Byzantine? Okay. See, so we're at 1/3 Byzantine. We're even at 1/8 Byzantine, right? So what's the point of trying to get higher than 1/8 BFT? But in a real world context, there's often lots of different reasons. There's economic pressures. There's various kinds of external pressures that might drive validators to act in ways other than strictly following the regular protocol rules. And so having a clearer picture of what it means to recover from 51% attacks from different kinds is, I think, also something that's very important from the protocol. I think it's also something that kind of academics may shy away from, because there's theorems that say that you can't, you fundamentally can't make a consensus algorithm that is resistant to 51% attacks. And a lot of the solutions that I'm going to show, they're not fully automated solutions, right? They depend in part on social consensus, but I think there's still this interesting question of trying to automate this process as much as possible. So trying to, not necessarily completely remove the need for social consensus, but still minimize it as much as we can, and really try to provide as much guarantees as we can, even under the conditions where more than half of validators are just doing something that we don't want them to do. So what kind of chain are we talking about, right? I think the chain that I'm kind of informally focusing on is present-day Ethereum, but the claims that I make are applicable both to present-day Ethereum and to future Ethereum after we add single slot finality. So after single slot finality, it basically, you'd be able to think of Ethereum as being kind of like this hybrid where you have a Tendermint-like gadget where in the events that more than 1/3 are offline, there's still a fork choice rule, so the chain keeps on progressing. And then also there's this other style of proof of stake called chain-based proof of stake, and some of the earliest proof of stakes, so Peercoin, NXT, and even some of the more recent ones are chain-based, and a lot of these things apply to chain-based proof of stake as well, right? So the main practical difference, I think, between Ethereum-style proof of stake and chain-based proof of stake is that there's this concept of a block and an attestation. A block is like a node in the graph of blocks, right? You just think of all blocks as being a tree, and a block is just a node. When you add a block, you're just creating a new node, and that block contains transactions. An attestation is the thing that actually gives weight to one block versus another block, and blocks that have more weight on them are going to be the ones that nodes kind of follow as being the chain, right? So, if 80% of people are voting one way, 20% of people are voting the other way, then the first way actually becomes the chain, and that's an attestation. And in chain-based proof of stake, basically a block is being this kind of node in a graph and a package of transactions and an attestation at the same time. And in Ethereum-style proof of stake and Tendermint-style proof of stake, those two kind of become separated, right? But that's the only difference, and I think a lot of the things that I say generally kind of apply across all of the different contexts. So types of 51% attacks, right? So just to get more concrete, what kinds of violations of behavior are we talking about, right? So the most common type of 51% attack that is in people's intuitions is what I call double finality, or what we call double finality reversion. This is basically just you have a block, and people think that block is final, and then somehow that block just gets reverted, and that block is not final anymore, right? So, you send me, $10 million worth of Dogecoin, I send you $10 million worth of Bitcoin, and then 2 hours later, poof, the Bitcoin chain somehow reverted, and you don't have your $10 million of Bitcoin anymore, but I still have my $10 million worth of Dogecoin. So this is the traditional scare story, right? That I think people tend to think about the most, probably since even 2009, right? And it's clear why it's the worst kind of attack. It kind of violates probably the most important guarantee that once you have something, you have it. And it's also clear what the economic incentive for it is, right? Because if you can revert transactions, then you can steal money from people. You can give money to people, and you can just yoink it back. Now, double finality is not the only kind of 51% attack, right? So if we could fix double finality, that does not mean that we fixed everything. And Ethereum proof of stake, style proof of stake in particular, makes double finality extremely expensive through the slashing mechanism, right? If you make a double finality attack, that means that 1/3 of all the validators, they double sign, they sign conflicting blocks, they get slashed, they lose millions of ether. It's extremely expensive and almost always not worth it. But there are these other kinds of 51% attacks that are still nasty, right? So the two main other kinds are one kind of consensus prevention, right? So preventing any block from really solidifying in consensus at all. Sometimes the phrase balance attack is used to describe this kind of attack. And another major type of 51% attack is exclusion. So basically preventing either all blocks that do not belong to the attacker, or just preventing some very specific subset of blocks from getting into the chain at all, right? Like blockchains have this important technical property that they're trying to achieve, which is that, if you send a block, you should be able to, and you follow the rules, you should be able to expect that this block at some point gets included. If you send a transaction, you should be able to expect that at some point the transaction gets included into the chain if it's valid and it follows the protocol rules, right? And we can kind of focus on specifically on blocks because, if you send a transaction, eventually there's going to be one honest block maker who's going to put it into a block, and so it just matters that like one block gets in at some point. And this is important for a lot of applications, right? Like there's even a lot of applications for which there is a security assumption that, if something bad happens, some actor who's the victim is supposed to be able to send a transaction containing a piece of evidence, and that transaction has a period of time during which it's supposed to get into the chain. And for those kinds of things to work, the blockchain just kind of has to satisfy this strong, unconditional guarantee that if you send a transaction and that transaction is valid and it follows the rules, then it should be able to get into the chain. So I am not considering going offline to prevent finality as a kind of attack, just because if all that you do is go offline, then I feel like the existing Ethereum design already kind of solves it, right? Like if half of the validators go offline, then, or even 3/4 of the validators go offline, this like mechanism called the inactivity leak kicks in, and their balances start decreasing until, once after their balances decrease by about 3/4, then, that 3/4 of all validators becomes a very tiny fraction, and the chain starts finalizing again, right? So if going offline is all that you do, then like it's an inconvenience, but it's extremely expensive to whoever does it, and eventually things get better again. So I think consensus prevention and exclusion are these kind of more dangerous categories because they can still lead to really nasty stuff. They still break like these really important guarantees, but they also are like they're not possible to prove, right? Like you can't, like from the point of view of just kind of an archaeologist node that's getting all of the information about what happened like 5,000 years in the future, you can't actually tell the difference between even like an exclusion attack and people going offline, right? Because an exclusion attack is in some sense kind of mathematically equivalent to pretending that a certain subset of messages came an hour later than they actually came in reality. So what do we do about them, right? I mean, so first, just important to remember, exclusion attacks can happen for a few reasons. So accidental software bug, right? So you could have some client that has some software bug, and it accidentally treats some subset of blocks as invalid, even though those blocks are actually valid. Accidental because of network partition or because of network delays. You could even have an attack on the network. You could have some incredibly weird and spooky thing happen over the global internet. If blockchains become systemically important to the tune of trillions of dollars, then it will become worth it at some points to try to do this kind of stuff. And I think it's very possible that like all major networks will kind of break once or twice before they have to like really adapt their peer-to-peer layer to become much more resilient. And the third option is intentional, right? Where the network is working fine, but some large portion, some majority of the nodes, just for whatever reason, could be economic, could be intrinsic, could be extrinsic, they just want to like, prevent some subset of blocks or some subset of other validators from being able to get into the chain. So double finality is easy to respond to, as I mentioned, right? It's expensive, you can slash the attacker, and there's this like very clear shelling points for when the community should respond. Like it's very clear when a double finality attack happens, and everyone in the community can immediately go on high alert, and it's really easy to see like when everyone should go on high alert. What about the other attacks? So one way that I think about this is look at what are nodes supposed to be doing, right? And in at least like the proof of stake protocols of the Ethereum-Style and of the style that Ethereum is moving into with single slot finality and with Even just single chain stuff, so Peercoin and like NXT, and I think even some versions of Cardano also chain based. The basic rule is you kind of build a test on top of the block that wins the fork choice, right? So the fork choice is a function that looks at the block tree. It looks at the tree of all the blocks that have been created, and it looks at the attestations, and it chooses, like by some mathematical metric, which of the chains in the tree is kind of most supported by the voting that's been happening. So in this particular case, if we just follow Ghost, which is what Ethereum is doing, right, then you start from this block and the block on the left, and you notice it has 2 children. So those 50 votes on the left, they're just voting for that block, so they don't actually choose between the 2 branches. Then if you want to choose between those 2, then you can look at, okay, so the one on the left has 35 plus 38, which is 73, and then the one on the right only has 13, so 78 beats 13, and so you go on the top, and then the one on the top only has 1 child, and so the fork choice winner there, like that's the head, and you're supposed to attest to the head, and you're supposed to build on the head, right? So there's like a natural kind of clear, correct behavior that's obvious from the point of view of nodes that are actually online. So claim is that a test on top of the block that wins the fork choice is a sufficient rule, right? So if most nodes do this, then you're not going to get balance attacks, and you're not going to get exclusion attacks, right? So if most nodes just like, be good nodes, and they just build on whatever the top of the fork choice is, then whatever block is kind of most strongly being voted for is going to be even more strongly voted for, and so the same chain just keeps on getting reinforced, it keeps getting lengthened, and everything works fine. You're not going to have like, weird balance and kind of, A going to B, going back to A, going back to B stuff happening, and you're also not going to get exclusions. The reason why you're not going to get exclusions is because if you're an honest validator and you just build a block on top of the fork choice winner, then you know that that block is going to be a fork choice winner, and so you know that most validators are going to attest on top of it, and so they're going to make your block also be the fork choice winner. So if most nodes do this, then we're basically fine, right? But if a node does not follow this rule, and this is this kind of important claim too, currently online clients, validators and users can tell, right? So the kind of hypothetical archaeologist 6,000 years in the future is not going to be able to tell. But currently online, validators and users are going to be able to tell. And basically, there's this mechanism called view merge. So the core idea basically is that if you have an honest proposer, then there's this mechanism where the proposer can kind of force agreement among all honest clients in terms of like which attestations they take into account. And if you force this kind of agreement, then all of the honest clients are going to see like the same inputs to the fork choice, therefore they're going to see the same output of the fork choice, and so therefore they're all going to converge on the same correct answer of what you're supposed to build on, right? So this isn't always true, right? Like if you have a dishonest proposer or if you have an absent proposer, then this is not going to happen. But whenever you see an honest proposer, you are going to have this situation where you have this kind of shared knowledge, not necessarily common knowledge, I'll get to this, but you have like some level of shared knowledge that this is a block that everyone is supposed to be building on, and you can kind of look at who doesn't, right? So if a client sees that some proposal was visibly published on time, then the client can see who did not attest to it, and they can mark those attesters as being suspicious, right? So a client that is actively participating in the network has some level of information about who is misbehaving. So problem is we don't have common knowledge, right? Basically, even fully online clients, in some extreme cases, they might not agree on who is suspicious. And this is especially true if you have a proposer that's kind of intentionally trying to break a kind of agreements about who is suspicious, right? Like basically, whatever your deadline is, you can have a proposer where they propose at such a time that from some clients' point of view, those clients see the proposer as that proposal as being on time, and other clients see it as not being on time. And so, if like, your proposer is Alice and they propose, and then, you have Bob and Charlie. Bob thinks that Alice was on time, and Bob thinks that, or Bob thinks Alice was on time, Charlie thinks Alice was not on time, and then they both see David's attestation, and David's attestation was wrong, then Bob is going to give David a suspicion score, Charlie is not going to give David a suspicion score, right? So there is this kind of unavoidable level of disagreement, and I think it's important, right? So there's this unavoidable level of disagreement, and I'll mention this later, but like there's good technical reasons why this level of disagreement is unavoidable. But the question is, so if we cannot fully agree, then what can we do? I think the kind of easiest idea that everyone tends to intuitively jump to is this concept of social response, right? Like if there is a clear 51% attack where really nasty stuff is happening, then we can coordinate a manual client setting that does one of two things. You can either hard fork whoever the attackers are that people agree on out of the validator set. And like I'd argue that this is politically risky, or you can soft fork them out, right? Soft forking them out basically means that you kind of basically if the bad guys are ignoring the good guys, then the good guys start ignoring the bad guys, and they start kind of just ignoring their attestations from the point of view of fork choice, and they could even start ignoring their blocks, right? And so basically what you would get is you would just get hopefully try to get this sort of clean split between, the good guy chain and one or more bad guy chains, and potentially in this kind of soft fork, like it could even reject finality, right? So, but even if you have a chain where, let's say, 80% of the validators they look from the archaeologist and the futurist point of view, like they're just constantly making new blocks and they're finalizing them. But from the point of view of like nodes that exist today, they're clearly ignoring particular blocks that they should not be ignoring, and everyone sees this. Then you could have this kind of publicly agreed upon soft fork to even ignore the finality, right? And basically just say, okay, fine, we don't care that you're 80%. You're clearly off in your own parallel universe. Bye-bye, enjoy. And like we're just going to be our kind of 20%, and we'll keep going separately. So I think to me the general trade-off here is that like the hard fork route is quicker and cleaner to execute, and soft forks lead to weeks of poor chain performance, right? So soft forks will lead to week-long, maybe even like up to month-long inactivity leaks and no finality. So soft forks are like a much less clean way of exiting from this, but in my opinion, this is kind of a good thing, right? Hard forks are like very easy to abuse, and they're like once you create this norm that you respond to things with hard forks, then like people start saying like, oh, I see, we have a norm that we're going to hard fork out any actor that we think is unethical. What other ethics rules are we going to invent in the next 2 decades? And blockchains kind of stop being immutable, and then someone eventually creates ETC 2.0, and then ETC 1.0 is like, what the heck, man, we were here first, and things go weirdly from there. So like that, to me, that's kind of the political risk of relying on the hard fork route. The soft fork route, like the fact that a soft fork sort of forces the chain community to endure this sort of like 1 month period of just like annoyance and low performance, kind of itself forces soft forks into being this kind of very exceptional category that's very difficult to turn into a regular thing and more difficult to abuse. So what if we don't have to do a social response? What if we can do a technical response, right? So this is kind of the big question here. And I think this is where like this presentation, and to me, is like, it's not about proposing a solution. It's about sort of proposing a problem and proposing what I think is an interesting open research area, which is technical response. How much can we automate the decision of when and how to recover from this kind of attack? Can we fully automate a response? And if we can't fully automate the response, can we partially automate a response? What does it mean to partially automate a response? So fully automating recovery from consensus failure implies solving consensus, right? So this is kind of the intuitive arguments for why we can't kind of just have a purely technical response that just does everything automatically. Right, because if all the nodes agree on whether or not you're supposed to do some exceptional procedure to recover from a 51% attack, then that means that you have a consensus algorithm that can somehow survive despite 50% of people, 51% plus of attackers trying to trick it. So let's go back and remember 1980s era consensus research. So this was a fairly famous chart from the Dwork-Lynch-Stockmeyer paper, 1987, I think. This stuff is also in Leslie Lamport's paper, so it's been around for a while, right? Basically, there are these kind of different modes of like what kinds of failures there are, and generally, like in practice, the column that matters is authenticated Byzantine, right? Like nobody cares about Byzantine because, like, come on, you can sign stuff these days, and like computers are powerful. Right, authenticated Byzantine just means you can sign stuff, and attackers are kind of the worst. Like, we're trying to assume the worst case. We look at the authenticated Byzantine row, and there's these kind of different modes, right? There's synchronous, there is kind of partially, and there's different kinds of partially synchronous cases. So in the synchronous case, right, there's this interesting fact that, like, well, actually, you can get 99% fault tolerance, right? And there's this kind of really clever algorithm for doing this. And basically, the idea kind of is like you take the view merge protocol and you just like repeat it n times, like you repeat it as many times as you want to get more fault tolerance. And the idea is that, like, if any one of the actors in these n steps is honest, then they kind of serve as a convergence point and they force agreement among everyone. But it comes with hard trade-offs. In particular, you need n communication rounds to achieve 1 minus 1 over n fault tolerance, right? So as a way of like automating agreement on whether or not a block is building on top of the next block, it's not actually very viable unless we want to have block times of like 1 day. Which, by the way, if you're kind of in the Bitcoin school of thought where like everything important should happen on top of the Lightning Network and channels should have 3-week closing times, you might actually want to consider like whether or not you want to just do it on top of a blockchain where the block time is 1 week and and the synchrony delta is like 12 hours and the whole thing is like resilient up to more than 90% attacks. Like, that might actually be the most robust blockchain you can do. Maybe someone should just like go build it, but otherwise, if we want more performance and we don't want to do everything with channels, then like this isn't great for like checking blockchain performance. But it is great for maybe it's great for like verifying that some transaction has been in the public mempool long enough, and like maybe you want to just have some protocol for verifying whether or not a transaction has been excluded from the chain for more than like, let's say 30 minutes, right? So if you set delta to like say half a minute, because it actually needs to be 2n communication rounds. Right, so if you set delta for half a minute and then it's and you set 30 minutes, then you have this kind of 98% fault tolerant gadget that lets you basically verify whether or not get really, really sure that some transaction existed in the mempool and therefore that it should have been included. So you can do something with this stuff, but like it's not perfect, right? Now, in partial synchrony, we can't exceed 33% fault tolerance, right? So generally, whatever technical response we have for recovering from 51% attacks, if you're offline, you're screwed, right? If you're offline, you basically have to like call up your closest trusted friend who was online, and that's just like the best that we can do, right? Like the goal is to do as well as we can. So if the 99% fault tolerance stuff comes with hard trade-offs, then like what can we do? Not very practical idea too. So this is kind of Vlad Zamfir has been doing a lot of work researching this. The idea here is kind of like this is kind of an honest clique approach. Basically, if if you know that you are honest and another validator fails to build on top of your block, then you start ignoring them, right? And you can show that after enough rounds of this, all of the honest people are going to not be ignoring each other, but all the honest people are going to be ignoring all the dishonest people. So eventually, you get kind of this convenient split into two cliques. You have kind of the good guy chain and the bad guy chain. The problem is this takes a very long time, right? Depending on like how you do it, it's like somewhere between n and n squared slots. With Ethereum-Style 100,000 validators, like this is just insane. So this is not very practical, but I think like building on top of this, open research area, I encourage it. But if we can't fully automate, what can we do, right? We can partially automate. So this is a kind of sketch for what might partial automation look like. So imagine if you're running your client and some kind of weird thing starts. It could be a 51% attack. It might not be. It might be some network thing plus a minority attack trying to trick you into thinking it's a 51% attack. You don't know, and you just get this warning, right? Possible network attack warning. A large fraction of nodes appear to be successfully attacking on a chain. Community members may be circulating a social response string. And the idea is that the SRS would just basically tell you, like, what are the details of the soft fork that you want to do? Like, which validators do you want to start excluding from the fork choice? And you would enter it, and you could continue with it, or you can just continue with the dominant chain, right? So nodes could maintain sort of local scores for how suspicious other validators are, and these scores might disagree because we know disagreement is possible, but we know that honest nodes are going to give other nodes, honest nodes, suspicion score 0, or at least very low suspicion scores if network latency kind of gets too high, right? So nodes can look at suspicion scores in order to locally give alerts and locally open up this box. So if there isn't a kind of a situation that looks suspicious, then nodes are just not going to give this alert, and clients are just not going to see an opportunity to enter an SRS. And nodes might even verify if a social response proposal is reasonable, right? So if you submit an SRS and that SRS kind of disagrees with what the node is doing, then the node might even give an additional warning. So like, basically, even if you can partially automate, right, like you can still kind of do these things, and you can kind of keep the human in the loop, but require the human to sort of be really in the loop and require the human to be more careful if what the human is kind of directing the node to do disagrees with the node's sort of guess of what is happening in the network. So what makes good partial automation? I think, so clients alone can't tell the difference between exclusion attacks and partial network partitions and other things. And so we need to kind of communicate this facts to users. We need to communicate to users, like, if some exceptional situation happens, what's going on. And another kind of good thing, generally good idea is, like, we need to maximally push users toward a few specific choices of when to kind of do these kind of social responses to kind of make the shelling point stronger, right? So like you might say, have a rule that says, we only activate a response at 1400 UTC every day, right? I mean, what's so special about 1400 UTC? Well, it's like the one time zone where enough people are online that you can reliably make like global Zoom calls then. So, might as well just stick everything into that time slot. So let's, now, you could go even stronger. You could say it's like once a week, 1400 UTC on Monday. Like there's lots of different ways to do this, right? So can we make, another idea is like, can we make the honest clique work, right? So take kind of, these honest clique ideas and like try to improve them, get convergence. Like the ideal goal that like I think may be feasible, may not be, that we're hoping for is to try to say, in as many kinds of 51% attacks as possible, just sort of make sure that eventually the good guys kind of semi-automatically or automatically converge on one chain, and hopefully the users just like see this kind of, like these kinds of dialogues where all that a user needs to do is sort of choose either one chain or the other chain, or if a user is offline, they might choose multiple chains that they have to follow. And ideally, even if it's not perfect for clients, and obviously it can't be perfect for offline clients, but still make it as easy as possible, right? So conclusions, I think, is that like one is we cannot fully automate recovery from 51% attacks. This is obvious. This is mathematically proven. But we can, I think, get a better and better understanding and kind of a better and better full topology of like what kinds of 51% attacks there are. We can reduce, I think, all the really serious failure cases to this one action of not building on top of the fork choice. We can get partial agreement among online clients about who is building on the wrong fork. And some level of manual response is still required, but we can really try to like reduce the level of manual response required, and we can try to sort of combine manual response with automated response, both to make it easier for users and to make it harder to abuse these kinds of response strategies to do anything other than recovering from actual 51% attacks. Now, how far can we go? I mean, it's an open problem, but I think it's like a really interesting and fascinating one. So, yeah.
Wait, Vitalik, there's questions. Vitalik, wait, come back.
Oh,
come back.
You thought,
We're not done.
oh, sorry.
Okay, fantastic. Thank you so much. Looks like a fantastic set of questions for the community to work on. I'm sure there are lots of questions, and we have time for 1 or 2 questions, so we might as well get started. Before we actually start with questions, though, just a quick announcement. Apparently, there's a black SUV. It's a Chevy Tahoe with New Mexico license plates that's parked in the back, and it's about to get towed. So if anybody owns a black SUV that's parked in the back, please go move it right away. So quick announcement. With that, let's turn on to, oh, I see people running out. Okay, so with that, let's turn on to questions. So go ahead, you're on.
Yeah, on the social consensus side of things, I was wondering if you have any ideas on modeling this and proving things about it and defining the properties that we want that are desired here. Is there a model that can involve a human and a sort of assumption that you can do some sort of honest communication socially that you can put in your math? Right.
That's a good question. I think it's very tough because, humans are complicated, and I think the mechanisms by which humans in practice even are honest enough to make civilization possible have not really been formally modeled by anyone. And so to some extent, I think you have to kind of be, very informal and sort of hand-wavy about some things. But I do think that there are things that you can try to model as you can try to come up with a kind of stricter notions of reducing the choices that are available to people. You can talk about what kinds of information different participants in the network see. You can talk about some notion that there is a social network, a social graph, and people have different kinds of trust assumptions. You could even try to model the idea of what happens if there's a 51% attack and some kind of attack on the social graph at the same time. I do think that there's a limit to how mathematical you can be because people haven't I haven't seen, for example, successful attempts at I don't know, using completely mathematical models to determine how vulnerable people are to just propaganda and misinformation on Reddit and Twitter, right? And to some extent, this is the same kind of problem. So I guess, okay, my conclusion is I think making that model and figuring out to the extent to which it's possible to make that model is probably part of the open problem.
Yeah. Let's take one more question so we have time for the lightning talks. So please go ahead.
Hello. I guess I would just like to know what the observational model is from one node to other nodes. As in, can you look at another node and say, based on the distribution of blocks that it is choosing to validate or vote on, that it's honest or adversarial?
Right. So what you can do, right, is you can make judgments that say, I saw thing X at time T, and therefore, if network latency is less than delta, then Bob's must have seen this at time less than t plus delta. The protocol rules say that if you see something at time less than t plus delta, you have to attest on top of it. Bob did not attest on top of it, therefore Bob is doing something wrong, right? So you can make inferences like that. You can, I think the more that you know about the network, the more that you can make inferences. I think network latency less than delta is just an incredibly crude model that's just easy to reason about. And then otherwise, basically what do you know, right? You know what the nodes are. You know that they have kind of they have fixed addresses in the form of public keys. You know kind of what their communication speed is. You know what they're supposed to do, and then based on that, I guess you can make different judgments.
Okay, I see.
Yeah.
Could you make almost a distribution over basically honest actions or actions that you perceive as basically bad that don't follow those rules?
Right.
And then say, oh, based on this confidence I have, I don't know, some beta distribution, this node is probably bad, so we should ignore them.
Yeah, I think using Bayesian models instead of hard deltas is definitely something that's totally worth looking into and doing here.
Got it. Thank you.
Great. Okay, so I'm going to jump in here, and we do have to leave time for the lightning talks. Vitalik, you're going to stick around. I'm sure, as you can see, there are lots of other questions for you. But now we're going to switch gears and switch to the lightning talks. And so, Benedict, the floor is yours.
Yeah. Thank you very much, Vitalik. Okay. Please make sure, just one thing before you leave. Please make sure we'll have the lightning session going on. Please be quiet in the back of the room and quiet when you're entering and exiting. And please also only exit through the back door, not the side doors. Because otherwise, it's going to get very loud and annoying in here. So. Can we get... Okay, so we're going to have the lightning session. All the speakers, please line up. I send out the slides so you know what the order is. The lightning talks are each going to be 3 to 5 minutes. And I will use noise to get you off the stage if you vastly overstay your talk time. So we're going to begin with Sergey from Chainlink. And yeah, it's going to be very exciting and a bunch of good talks. Thank you.
Great. Thanks, Benedict. Hi, everybody. So I'm here to speak about oracles and the change that they're making in our industry. The thing that I think people need to understand about oracles is that they are a form of creating cryptographically guaranteed truth. So in some of the talks you heard about today and even the previous one, you might have seen that there needs to be a certain truth about different actors. And actually, the notion of truth is very important in deterministic systems generally. So what oracles do is they create cryptographically guaranteed truth to solve very specific problems. They don't necessarily result in creating block space or processing payment transactions, but they do inject a cryptographically form of verifiable truth that allows systems to function correctly. And even some of the previous talks you've heard today and yesterday, the very specific problem that they were trying to address was defining and identifying what was true about an actor like a node or about any other thing such as a piece of data. What we do at Chainlink and the body of work that we're involved in is creating cryptographic truth around a multitude of topics that enable entirely new industries to come to life, such as DeFi. The first category where we've generated the largest amount of cryptographic truth is basically market data, which gave rise to DeFi and led it to grow to over 200 billion. Then we moved on to compute and other categories. Generally speaking, the way I view what we do with oracles and what oracles are more and more is as truth infrastructure. And once again, in deterministic systems that need inputs and that need things proven to them, there needs to be a truth infrastructure to allow them to interact with the world in an accurate and reliable way. At this point, we've put the largest amount of data on chain ever, once again resulting in the rise of DeFi on multiple chains. Right now, this data is being put on approximately 14 to 16 different chains and environments, with more and more on the way. The Chainlink system has also been widely used. So in addition to putting the data on, it gets regularly used by various different categories of applications, from gaming to DeFi to others. And once again, these applications can't work without cryptographically guaranteed truth, largely in this case based on market data, but expanding to many, many other categories. The category that we expanded to next was random number generation. And in many chains, we've become, the Chainlink network has become the most widely used source of randomness as a source of truth about a random event or that something is actually random. The ability to scale all of this data, all of these randomness requests, all of these compute functions, and soon cross-chain communications is based on us being able to make over 1,000 simultaneously running production committees. So when you hear people talking about making side chains or shards or subnets or parachains or any other category of scalability, that is basically making smaller committees that execute specific application code or specific application block space. And I'm very proud to say that we have been able to generate and run simultaneously and are now running simultaneously over 1,000 of these committees about various categories of cryptographically verifiable truth, enabling hundreds of billions of dollars in value. The body of work that we're engaged in is really around inventing new cryptographic protocols that generate this cryptographically verified truth for more and more categories of truth, whether that's random number generation, data, cross-chain communication, proving the reputation of a node, or any other category where a very specific thing needs to be true in order for a system or an application to exist. We then provide and have also invented the Oracle network environment, which can really be viewed as a general purpose, trust minimized computing environment that does all the trust minimized computation that needs to be reliable, but which a blockchain cannot do. And while that starts with data, it then expands to compute like randomness, and then to bridges, and then to many other categories of compute, because it's all really the same thing. It's trust minimized computation. And then our fundamental goal is to allow other people to build all of these protocols in this trust minimized compute environment, and to build the largest community of people building these trust minimized computations that enable other applications working on blockchains. So injecting very specific cryptographically guaranteed truth about a cross-chain transfer, or a piece of market data, or a random number generation event, or even a specific user-defined computation. So this is the body of work that we're engaged in. We invite you to come work with us. We have a table out back to discuss with researchers and other people. We have huge investment in research and development in our team. And frankly, both the Oracle network environment that we invented, and the data aggregation methods that power DeFi, and the random number generation system that now powers the majority of blockchain gaming on many chains, was all invented by us, by our research group, led by Ari Jules as our chief research scientist, and Dalia Malki as our chief research officer. So if you have interest in working on a general purpose, trust minimized computation environment that solves all these problems and injects cryptographically guaranteed truth into the world, then you're very welcome to speak with me at the conference. You're very welcome to speak with the people out back at the table. And if you make an application that needs a very specific trust minimized computation, then I encourage you to look into this as a solution, because it's what has allowed DeFi to grow to where it is, and it can probably solve your problem as well. So thank you very much.
Thank you. Okay. Thank you. Okay, next up, Nick's Whistle.
Hey, good afternoon. I come from the usually non-believer world, which is enterprise. This is my second venture. We have built a product in the governance, risk, and compliance space, automating the cybersecurity standards for past 10 years. This is my second venture. We are the Web 2.5 of the enterprise world because we are still have done this in the private blockchain. Our mission is to make the world transparent and inclusive. We have got ethics blockchain, which is helping organizations to streamline, which is a very important process, which is whistleblowing. All of us know the last week's whistleblowing of the Twitter security officer. All of us might have heard about Theranos, Uber, WeWork, whatnot. I think we have many stories. Let's see how we are trying to automate with the help of private blockchain. We are trying to provide a system for both board and employees to see how we can do tamper-proof investigation and also incentivize for the right reports. Dr. Martin, he's a senior technical fellow in a large corporation, reported about an issue of a quality of a multi-billion-dollar product to his manager. It was not listened properly. He went to his CEO. It was not listened properly. The report got tampered, and it led to 346 deaths. 346 families lost their loved ones. $2.5 billion penalty will not bring those lives back. It happened in Boeing. And we have seen, I think, Uber, WeWork, Theranos, where employees were hesitant about reporting about abuse. And we have seen even banks paying $336 billion as penalty over 7,024 reports in the past 22 years since the regulation Sarbanes-Oxley came into existence. So European Union is the only one who have thought about this, even come up with a regulation to protect employees trying to become whistleblowers for even 50+ people corporation. 10 member countries have already enacted this as a regulation. This is the next GDPR in action. SEC is taking inspiration from this, improving its environmental, social governance disclosure requirements. Our solution has a large market. Usually it's called ethics reporting, and where organizations even classify this under governance, risk, and compliance. This is primarily towards large corporations who are worried about leakage of fraud, waste, abuse reports. And it's a very well-proven market. Nevex Global is the leader, and they got sold for $1.4 billion 5 years before. Our solution solves both the problems of employee as well as employers. Employees have this usual skepticism of organizations tampering their reports and retribution. So our ethics chain is solving by providing tamper-proof and anonymous incentives. And management has the signals versus noise issues. Not all managements are corrupt in nature. They are having huge volume at times. They don't know which is a good report and which is this usual HR human resources report. That's where we have some intelligent prioritization, which helps handy. And yeah, I think we are in business, and we kind of have put a seed round together, and looking forward for your support. We are collaborating with a few of the Stanford talent. Looking forward for talent who is keen to work on a private blockchain project, which is interesting. Thank you.
Thank you very much. Please always make sure to click to the next slide. So, okay. Who's up next? Thank you. By the way, for next time, it is usually customary at these presentations. It's also very much allowed to give funny and joke and hilarious talks. Usually that involves a little bit of alcohol, but maybe we'll put this session in the evening next time. Just saying. Anyway, keep going.
Thank you. So we have a problem in the programming language and tools community, namely that we want both lots of languages and lots of tools for them. And each of these combination of a language and a tool is a complex system, and there is a lot of duplication in our work. We implement model checkers for lots of languages, formal verifiers for lots of languages. These duplicate code. These have bugs. So the K-framework proposes to separate concerns. K-framework provides state-of-the-art implementations of well-known formal verification, and not only tools, execution tools, model checking tools, symbolic execution engine tools, in a completely general, language-agnostic way. And then also allows you to define your programming language as a parameter to the tool. And then you can plug and play your language in the tool. So if you want a formal verification tool for Ethereum, then you plug and play the mathematical model of Ethereum. And this is the infrastructure in which you can build tools. For example, you can build execution engines, virtual machines, testing tools on top of certain tools in the back of the K-framework, like the interpreter and compiler capabilities. You can build optimizers or MEV analyzers, like we saw in yesterday's talk, on top of the exhaustive search space exploration tools, like model checking. And then we can prove formal verifiers on top of the symbolic execution and deductive verification tools. And what is interesting in the context of K is that computation is literally proof. So the fact that the program computes is the same as proving a theorem in the K-framework, which means that you can check computation by checking proofs. So you have a more general way to check not only computations, but also results of formal verification, results of model checking, results of everything. And because of this generality, the proof checker is unbelievably small. The proof checker has only 250 lines of code, and with this proof checker, you can check any property about any program in any programming language, including computation. If this sounds intriguing to you, we have all our doors open. We are looking for collaborations on the research side. If you are interested in sponsoring our research and our work, you are welcome. If you want to use our tools or want us to use our tools to verify your smart contracts, or if you have a crazy new programming language that you like to have all these tools for, contact us. We can plug and play your language into the framework, and you have verification tools, you have model checkers, you have execution engines, VMs for your language. And we hire, so if you want to work with us, you are welcome. And if you are an investor interested in changing the world this way, please contact us. Thank you.
Thank you. Okay, whose slides are these? Well, I guess we'll go to Marky. Okay, Aline from Aptos is next.
Hi, everyone. I'm Aline, and we are Aptos. We are a layer 1 company, so why might you want to hear about another layer 1 company? 3 reasons. With Aptos, we offer performance, security, and upgradability without sacrificing decentralization. So on the performance side, we have a pipeline, highly optimized consensus algorithm. We do parallel execution of transactions using optimistic concurrency control. On the security side, we have a new programming language called Move. So you can think of Move as a Rust-like programming language with linear types. And importantly, Move supports formal proofs about your smart contracts, so you can prove certain invariants hold. And we support users efficiently rotating their keys while maintaining the same address. And at the same time, we have upgradability, which means that in Aptos, you can deploy a smart contract and later on upgrade it while maintaining the same address and while maintaining API compatibility. The reason I'm here is because we are hiring on 3 fronts. On the research front, we need applied cryptographers. On the distributed system side, we need distributed systems folks. And of course, we need engineers because research is overrated. So on the applied cryptography research side, we are doing exciting work in authenticated data structures. So for example, we're working on very short Merkle trees or Verkle trees. We're working on Merkleized log-structured merge trees. We're working on bilinear or RSA accumulators. We're doing work on signature schemes, multi and aggregate signatures, ring signatures, group signatures, on zero-knowledge proofs, range proofs, set membership, zero-knowledge proofs, generic proofs, and so on. And many other cryptographic fantastic beasts like oblivious PRFs, broadcast encryption, distributed key generation. On the distributed systems side, we are working on DAG-based consensus protocols like Narwhal, Tusk, and Bullshark, on parallel execution. So BlockSTM is the work that we've deployed in Aptos, for example, and on sharding. So thank you so much. Check out our website, and my Twitter is down here. And also, we are having an event today at 6 p.m. Feel free to check out my Twitter. It's also announced there. Thank you so much.
Thanks, Aline. Reversion.
Can everybody wave to me? All right, cool, thank you. I just need to make sure that my boss knows that I'm not here just to blow the per diem, so. All right, all jokes aside, thanks for being here. My name is Ieee. I'm the Senior Solutions Engineer for North America BNB. I'm here to present a community-oriented security initiative called Avenger DAO. Avenger DAO is a multi-component API-based system providing BNB users and participants with a layer of security against scams, rug pulls, and malicious actors. So the Avenger DAO consists of 3 main components in addition to the DAO governance structure. The meter, which is a passive API where requests for security audits of contracts and transactions can be made ad hoc. The watch, a subscriber-based active API layer, which is intended to send out real-time alerts to subscribers. And the vault, which is an escrow-type service that transactors can use to lock up funds to guarantee the safe passage of those funds programmatically. So currently, we are in the process of building these API layers, and we're looking for audit providers and partners to work with us to provide those audits. Anybody that's interested in also helping wallets, exchanges to provide these security countermeasures, and anybody that's also in the blockchain security space. You know, it's a very niche space, and I'd love to hear from you guys. I'd love to connect with you guys. I'd love to talk with you. My BNB team is actually here today. My education director, Yuteng, please raise your hand. Please connect with her if you guys would love to learn more about BNB or the initiatives that we have, and please feel free to connect with me as well. Thank you, guys.
Thank you.
Hi, I'm Naomi, and I'm an intern on the Quilt team at Consensus Mesh this summer. And I've been working on a project, it's the Ethereum execution specs, and if you guys aren't familiar with that, it's just a description of the Ethereum blockchain and virtual machine, which can be run as a program. And it's written in Python for simplicity and readability. And I'm going to be giving an after-hours talk about it today at 5 p.m. in the back room of this building. So if you guys want to come watch, please do. I'll just be kind of giving a tour of what the execution specs look like, why they're useful, how I helped on the project. So here's an example of our generated documentation that we've been working on, and it just provides, we're trying to provide a combination of a snapshot of Ethereum at each hard fork, which is similar to the yellow paper, as well as preserving the idea of patches or EIPs. So as you can see in the generated documentation, there's the red side for the Frontier hard fork, and then the green side for the Homestead hard fork, and that's the diff. I think this is EIP number 2. And it also tries to simplify the yellow paper in order to make protocol easier to understand for developers and users in general. And then here's an example of what the code looks like at each hard fork, if you want to see. Kind of similar to the yellow paper, just see a snapshot of what Ethereum looks like at each hard fork. So I'm going to be giving the talk today at 5, again in the back room, if you guys want to come watch that. Thank you.
Thank you very much. Nusret?
Hello everyone, I am Nusret, and I would like to introduce my new paper, Cryptoeconomic Security for Data Availability Committees. This is joint work with Professor Dan Bonnet, and you can find the paper at the provided link. Many layer 2 systems increasingly rely on off-chain sets of nodes called data availability committees to persist the relevant data. So they give their users the option to choose between putting data on-chain and storing it off-chain in a data availability committee. But this requires the users to interact with the data availability committee to recover the relevant data if they need it. To ensure that this data will be recoverable, many of these projects assume that some fraction of the data availability committee will be honest. However, in our paper, we would like to go beyond this honesty assumption because, as Vitalik just talked about, there can be 51% attacks, and we would like to provide a trust-minimized crypto-economic notion of security that relies on incentives to discourage censoring data availability committees. For this purpose, we envision an on-chain contract where the users can complain if the data availability committee censors or do not reply to their queries. Now, this brings up a plethora of questions. For instance, how do we ensure that the data availability committee replies to queries on-chain? So for this purpose, we would like the data availability committee to be staked on-chain. But what would be the optimal slashing function if they misbehave? How would we characterize an optimal contract? So if you are curious about the answers to these questions, you can check out our paper. And we assume bribing adversary in our paper that can offer bribes, and we model these data availability committee members as rational nodes. And as you can see here in the given parameterization, we found that the optimal contract actually offers good security, as it would require the adversary to spend $4 million in bribes to violate security even by a small fraction. Thank you very much.
Thank you, Nusret. Thank you, Nusret. I think you can adjust the microphone, by the way. Anyway, Zendesk, anybody feels responsible for these slides? No? Okay. And we'll skip through them. ETH does numbers. Thank you.
Hey guys, I'm Nolan, and this is
Hi, I'm Sampriti.
We're undergraduate students, part of the 0xSpark community, and this summer we've been hacking on recursive snark-related applications, and one of the applications, or at least one of the properties that is really cool about recursive snarks is this idea of composability, where you can essentially send people proofs and they can build on top of it, and you can sort of additively add more knowledge to a small constant-size proof. Using this, we ended up building a project called ETH during ETH New York Hackathon.
Hi, so yeah, what we wanted to use was like use the property of recursive snarks like Nolan mentioned to make kind of like a social experiment type game. So if you guys have heard of the thing called like 6 degrees of Kevin Bacon or like the Erdos number where you try to find like how connected you are to someone. So we kind of wanted to replicate that on the Ethereum blockchain or any blockchain for that matter. So for example, what we do here is we have like an origin person, like in this case it's Adhayan, and then he can send out like proofs to other people and it's like kind of like a proof of friendship, but like that's what we use recursive snarks for. And then that person can repackage that proof as like in a recursive way and send that to someone else. So for example, from Adhayan, the proof can go to like Nolan and he can like mint an NFT that says like, oh, I'm a 3rd degree friend or I'm like 3 degrees of separation away from Adhayan. And the cool part about this where we use the ZK properties of recursive snark is that Nolan won't know how the chain got from Adhayan to him, and like that's kind of like the interesting part that we want to build as a social experiment here.
Yeah, so we'll be at the Applied ZK workshop later this week on Friday, and also we'll be releasing some prototype of ETOS this weekend. So we have our Twitters and those kinds of things, so hit us up. Thank you.
Thank you.
Thank you. Next up, MobileCoin.
Hello, I'm Chris Beck. I'm a principal engineer at MobileCoin. I'm here to tell you today about MobileCoin Fog. So MobileCoin's mission is to be digital cash. We want to be fast and secure. We're designed to be integrated with messaging apps like Signal. Our goal is that transactions should fully complete in 5 seconds on mobile. So there are many private cryptocurrency projects out there, but right now MobileCoin is unique in that we support a fully private experience on mobile devices without trusted third parties, and Fog is our key to this. So let me sort of explain the fundamental problem. So to my knowledge, all private cryptocurrencies are based on Bitcoin's UTXO model, and there are good reasons for this. But this creates a huge problem on mobile, which is how do you find your TXOs if you're on a mobile device? The basic problem is that you cannot sync the entire blockchain on mobile, pretty much for any chain technology, because it's bandwidth prohibitive and it's also CPU prohibitive if you have to match private keys against transactions. So most projects approach it from the point of view of trying to do a thin wallet. So you give away your view key to a mobile app service, which then scans the blockchain and filters things on your behalf. But then the problem is that you're trusting the provider for your privacy. They can see which transactions are yours, they can see when you get paid, they can see all kinds of stuff. And so this is a non-starter for an app like Signal. And MobileCoin Fog is our solution to this. So Fog is an oblivious data pipeline which privately indexes the MobileCoin blockchain and then makes it privately searchable for the users so that they can recover their balances quickly and easily. The selling points here are that when you use Fog to sync your balance, you only download your own TXOs. You don't download everybody else's TXOs, and this makes it very fast and bandwidth friendly. But because we've designed the system to be oblivious, we have no idea when you sync your balance which TXOs you download, or even if you downloaded any TXOs. So this preserves your privacy when you use the system. Importantly, your private keys never leave your phone. You never have to send them to a remote service. We have a really important property called break-in recovery for SGX. This is basically a self-healing property. Our threat model is the same as Signal contact discovery, so we don't assume that SGX is always secure. We assume that SGX may get broken at some point, and if it does, we have to patch the servers and redeploy, and then users don't have to rotate their keys and privacy is restored. Finally, the service scales gracefully to millions of users. It's horizontally scalable. We've served millions of RPC requests in a day with 2 nodes. These are oblivious search requests over the entire MobileCoin ledger. So the key technical component that makes this possible is an implementation of oblivious RAM inside of SGX enclaves. So this is really interesting because there are not a lot of examples of private information retrieval being used in real life in the real world, because a lot of them are not performant enough to be used in practice like this. But we spent years working on this and optimizing this. To some extent, we co-designed the blockchain with the oblivious RAM implementation so that they would work together. We actually load the entire blockchain into oblivious RAM. And this is the first time that oblivious RAM has been used in a production web service. If you'd like to find more information about this, so we've been in production in Signal since February 2021 for the Signal payments beta. You can find our white paper at mobilecoin.com for Fog. You can also see our code at the GitHub repository. We have a Trail of Bits audit report, and please look for our detailed technical report coming soon. And if you'd like to chat with me more about this, I'm going to be at the conference the rest of the day.
Thank you.
Hey everyone, my name is Sarish and I'm a first year PhD student at Duke University, and I'm going to be talking about the overarching theme of my research, which is role of incentives in decentralized protocols. So this is based upon our recent work with my advisors, Fan Zhang and Karthik Nayak. Okay. So when we're designing a decentralized protocol, the main challenge that arises is to identify the players in the system, identify the sources of their income, and based upon that, make the action space correct. So for example, when we're talking about a general blockchain-based protocol, the two income sources that we generally look at are the payments from the users and the block rewards. And a third income source, that is the MEV, is usually missed out. And if this MEV is not considered while building the protocol, there is all sorts of incentive attacks, as we looked at in the morning presentation by Ieee regarding MAD HTLC. So just to recap, in the MAD HTLC, they broke HTLC by using a bribery attack in which Bob is trying to pay Alice some amount of money. If Alice reveals a secret, she gets the money, otherwise Bob gets it back. The problem with the underlying protocol HTLC was that Bob could pay miners to ignore Alice's transaction, and therefore the miners were not considered as a model. MAD HTLC corrects that by introducing the miners as a player, and what they do ensure is that if Bob ever tries to bribe the miners themselves can take away all the money from the HTLC contract, but not just that, they also take all the money from the collateral contract, which otherwise was going to go back to Bob. The problem here is that miners are actually not given their full potential. The miners themselves can bribe the player, which is Bob, to actually get back more money, because this adds another income source for the miner himself. We call this kind of a bribe as reverse bribery, and we present that in our paper that this is actually a big problem. Further, we present HEHTLC, which is actually correcting the action space as well. So our protocol is not only secure against active miners, but it is also very cheap. Like the collateral that needs to be deposited is very low. It's lower than the deposit amount. It's user adjustable, as in you can choose how much you want to lock the timeout that you want, such that if you have a long timeout for your collateral, then you can deposit lower collateral. And it also, yeah. So do check us out. There's a blog post on decentralized thoughts, and our paper is there. Okay, thank you. Thank you.
I think it's the next slide. Sorry, green. I just want to share 3 minutes about, 3 minutes, correct? About the IEEE Blockchain Initiative. So I'm a co-chair of the Blockchain Initiative. So if you haven't heard of IEEE, it's a nonprofit organization. It's the largest technical professional organization with 400,000 members in 160 countries. You can see the, number of articles, standards, 1,200 standards. Wi-Fi is an IEEE standard, Ethernet, Bluetooth, they're all IEEE standards. So I just wanted to share about blockchain initiative. It's just easy to go there. It's just blockchain.ieee.org. And you can see there's several activities. One thing I wanted to share is we have launched about 50 blockchain groups all over the world. So if you would like to get involved, or if you want to start a group, you can just talk to me today. And these are some of the highlights. We've been organizing conferences since 2018, IEEE Blockchain Summit and so on. And 2022, we have an event that's happening in Santa Ana, California. So if you would like to publish papers, submit papers, you're welcome to submit papers. It's in November, 7 to 11. And then also we have several educational content, tech briefs, standards, and basically you can go to this website I showed you, blockchain.ieee.org. You can get all the information. There's one last slide. Yeah, this is one thing we've been working on is we are working on how to integrate blockchain for transactive energy. So we have funded like 5 proof of concepts. They're trying to integrate the hardware and software in terms of creating a community-owned grid. If you want to know again, just reach out to me. My LinkedIn is there. My email address is there. Thank you for the opportunity.
Thank you.
Hi there, I'm Ron Bodkin. I'm co-founder and CEO of a startup, ChainML, and I'm going to tell you a little bit about what we're working on. We are working on the intersection of machine learning and Web3. So first question you may be asking, and specifically, like, how can you do things like integrate machine learning computation into smart contracts? Why might you want to do that? Well, it turns out there's a lot of use cases where it's really valuable to go beyond what you can do in simple programming, like detecting things like fraud, right? Or predicting volatility in pricing, right? That might be used for more efficient pricing of DeFi assets, or risk scoring for under-collateralized loans, or portfolio management on chain. Recommendations in content moderation in social protocols and around marketplaces, or perhaps in future the metaverse. And indeed, as you think about moving from simple airdrops to actual attribution of who's adding value to a network, machine learning could be really powerful for that. So we're seeing a lot of interest in how one might actually, what might want to use machine learning for. Currently, there's a lot of challenges, right? It's really compute intensive. Some people might say, we've seen prototypes saying, oh, well, we think with zero knowledge proofs, we can prove the use of machine learning on chain. We're very skeptical. There may be a role for zero knowledge proofs, but not convinced that real world models that are taking hundreds of milliseconds of computation are going to work well in that mode. Likewise, the data, right? The reality is the amount of data you need in order to execute machine learning models can be massive. Gigabytes just for model weights, and you may use large amounts of context. And, what the alternative is today is often Web 2.5, a centralized service that you try to hide and not talk about, but we think that destroys the value proposition of Web 3 and blockchains, right? You can censor it, it's not transparent, doesn't scale, it's at odds. So, today people are avoiding it. We're working on how to allow practical approaches, right? How do you trade off security versus overhead? How do you allow for economic and or technical security, right? What are ways to have simplicity and adequate latency? We're working on approaches to probabilistic detection of bad behavior in generality. So, we'd love to talk to you. We're hiring. We're just closing our initial funding round led by IOSG with, Chainlink as an investor and SNZ who's here at the conference and HashKey who's here at the conference. So, love to talk to people who are interested in the research or potentially interested in the space. So again, Ron at ChainML, thanks for your time.
Thank you very much.
Hi, everyone. This is Xiaohan Zhu from Meteor.io. Today, I would like to share a fresh perspective on proof of work, proof of stake, and the consensus design of cryptocurrencies ahead of the upcoming POS launch, POS merge for Ethereum. So if you look at all the existing native cryptocurrency designs, there's actually 2 consensus going on in the system people that normally do not realize. The first consensus is what we typically talk about. It's the record-keeping consensus, is to secure the ledger, replicate the states across different machines. So this is a computer science problem and can be typically done very efficiently with the right algorithm. But there's another consensus that's implicit. It's an economic consensus on the value of the newly created cryptocurrencies. This is an implicit consensus and can be fundamentally difficult and power-consuming. So in a proof-of-work environment, this is achieved by the competitive behavior of the proof-of-work miners. And also, proof-of-work have an interesting characteristic. It's strongly linked to the competitive price of electricity. And electricity price happen to have another interesting characteristic. It's really stable in terms of purchasing power over the long run. The chart actually shows over the last 70 years, it's more stable in terms of purchasing power than any fiat currencies in the world. So at Meter, we believe there's actually a more elegant way to redesign the consensus to clearly separate the record-keeping and economic consensus through proof of work and proof of stake techniques. And it's similar to the real world that the creation of money is always separated from the states. We have set up, also we would like to leverage the proof of work characteristic to create a non-custodian, non-collateralized stablecoin that can be sustainable. So we set out to perform this experiment through our mainnet from July 2020. So here is the architecture we have. So it's a dual chain architecture. At the bottom, we have a proof of stake chain that maintains all the addresses, all the states and account system. It's running hot stuff consensus with block by block view change and fast finality. And also, it is Ethereum compatible with some additional characteristics like front-running resistance. We have a side chain that's a proof of work only focused on creating the meta stablecoin for we use as payment in the system. And it brings additional benefits like completely permissionless and notion of time to the system. So here are the results over the last 2 years. So on the meta stablecoin side, you can see the price chart. We just launched it to the wild without any interference. You can see the price oscillate around a long-term average and maintains purchasing power relatively well, with some occasional spikes to the upside compared to most non-collateralized stablecoin. The spike is always to the downside. That happens to be during a period people get confused. We have a two-token system, and they bought the wrong token essentially during the period. And on the consensus side, currently we have more than 280 consensus nodes in the network. It's scalable to like a couple of thousands within the active consensus committee. Fast block period. And also in proof of work, people are always concerned about the hash rate attacks, right? We have seen hash rate swing from 16 petahash to 100 megahertz, and the system performs smoothly and maintains security of the system. So right now we have proved that miners, stakeholders, and developers can work together with the right tokenomics to build an ecosystem. And we'd like to invite all the developers to participate. Thank you.
Thank you.
That's for, oh, okay. Programmable interoperability. Imagine if we were able to make smart contracts react to off-chain events, to arbitrarily communicate with other blockchains, and to fetch data from the internet. Well, that's exactly what we are doing at Nexus, which is a new startup that originated from the Stanford Blockchain Club and from research at the Stanford Cryptography lab with Dan Bonnet. What we're working on is decentralized cloud computing for blockchains, and what that exactly means is we're building a new technology that we call decentralized cloud functions. And decentralized cloud functions are made to create programmable interoperability between smart contracts, meaning arbitrarily connecting any blockchain with the internet and in between themselves. And we use new technology that we developed at Stanford, including large-scale Byzantine consensus, multi-party computation technology, and the goal is to achieve the dream of blockchain interoperability with the real world in a programmable way. And the purpose of this talk is, well, to announce this to any Stanford students or engineers. We are hiring. We closed a well-funded seed round. Yeah, just go check out our domain. And if you are excited about the future of interoperability and actually making smart contracts useful, please check out our domain and, well, have fun reading our light paper. Thank you.
Thank you.
Hello, everyone.
Yeah, my name is Marek Olszewski. I'm from Cello, and today we're going to be talking about Plumo. You can find me on Twitter at Marek _. So 2 years ago at SBC, I was up on this stage talking about Plumo, which at the time was the design for our zk-SNARK-based like client protocol that we used for, we were preparing for the Cello blockchain. And I'm excited to share today, fast forward 2 years, that Plumo is now live. Woohoo! And this is pretty exciting, especially for us. And it's so exciting that I wanted to actually show a demo of it today. So I'm going to be praying to the demo gods in just a second. Special thanks to all of you who participated in the ceremony. This was a truly massive ceremony. Tens of thousands of hours of CPU time went into this. This was one massive circuit on BW6, which is a massive curve. So thank you again for those who participated. So today we now have a Plumo prover that is running, is generating Plumo proofs once a day. You can download these proofs and verify them with a WASM-based library, which means that you can verify these proofs in a web app and a mobile app. And of course, if you can verify these proofs, you can get the latest state root commitment on Cello, which means that you can use Merkle proofs to verify any state in the Cello blockchain. So pretty exciting. And with that, I'm going to switch to the demo. So this is it. I'm going to reload this, pray that the conference Wi-Fi works. So this is, again, a live demo. I'm going to unlock my web wallet using, this is the Cello web wallet. And the second I press enter, it's going to start downloading multiple Plumo proofs, I think 4 Plumo proofs, which are each about 1 kilobyte in size. It's going to verify these Plumo proofs, again, in the web browser, and then do 4 Merkle proofs to verify the account balances of each of those 4 assets. So as you saw, that took just under 2 seconds on conference Wi-Fi. It's pretty freaking exciting. It's a web wallet that's connecting on an EVM chain using a light client in the web browser, fetching data and verifying it in a truly trustless manner. So I can't wait to see what people build on top of this. I think there's lots of really interesting censorship-resistant and trust-minimized applications that people can build. I'm around if you want to chat. Yeah, we're excited. It's live.
Thank you very much.
Hi, I'm Ujjwal. I'm a first-year PhD student at UC Berkeley, and I'm going to give a talk very briefly about our new work on an optimistic rollup system called Specular. And this is joint work with another grad student, Je, and also Don Song. So as many of you know, optimistic rollups have been proposed as one potential solution for scaling Ethereum. And I won't go into the details of how they work here, but the key thing to understand is that the current state of the art aims to achieve a property called EVM equivalence, which means that the client implementation of the rollup and the client implementation of the rollup fully complies with the Ethereum formal specification. And so to achieve this, they reuse get at L2. And during a challenge, 2 participants execute an interactive fraud-proof protocol in the context of the compiled get binary. And eventually, one party has to prove a state transition at the instruction level of the compiled get binary. And eventually, one party, so basically, the verifier enforces the correct execution of the client program without really knowing what it does or whether it actually follows Ethereum semantics. And so this has a few problems. You now have a large trusted computing base, which is difficult to audit, and more so because it's updated frequently and less transparently than the Ethereum specification itself. And then the second problem is that client diversity is not naturally and permissionlessly supported because 2 different implementations can't generate fraud proofs against each other.
Yeah, so our solution is that we propose a new rollup architecture that is EVM native, where the one-step proof is performed directly at the EVM instruction level instead of at the target ISA level. And in this case, the verifier enforces the actual semantics that we're interested in, and not a specific client program that allegedly implements these semantics. So now we have a minimal TCB that includes only the verifier, and the client program is not included. And so auditing security becomes much easier, and it's something you need to do less frequently because Ethereum doesn't hard fork that often, although it will kind of soon. Yeah, secondly, we now also have very natural support for client diversity. And the verifier, and the reason for that is the verifier isn't tied to a specific client implementation, so every client can generate the same one-step proof. Yeah, and so we've implemented this approach in a new EVM native rollup, which we call Specular, and it's on testnet now, so you can visit these links. And yeah, please reach out if you have any questions or comments or feedback. Thanks.
Yeah. Now from one SBC to another SBC.
All right, hey everyone, I won't take too long. I'm Priyanka. I'm here to talk about the Stanford Blockchain Club, the other SBC. We're a student organization, just a bunch of students, right, from undergrads to postdocs. We just come together, discuss all things blockchains and cryptocurrencies. Let me do that. We have three main verticals. We have an accelerator where we incubate companies with Stanford-affiliated co-founders. We have a research program where we just come together, discuss interesting topics, and we use that research to eventually apply for our governance sub-vertical, where we do a whole bunch of proposals and votings for various protocols. We also have events and education, where we just spread the word, reduce a knowledge gap, and yeah, just have fun learning new things. This club is not fully close to just Stanford students, so even if you're not a Stanford student and would like to participate in certain aspects of it, which is open to everyone, feel free to check us out. This is our website, which has our mailing list and Discord, where we post almost everything that we pretty much do. And yeah, hope you had fun during this conference, and see you guys around. Thank you.
Thank you very much. Next up, Daniel.
Hello, everybody. My name is Daniel, but I usually go by Olshansky. And today I want to talk to you about developers, and remote procedure calls that they like to make. So in the top right here, we have what the original Bitcoin white paper promised us, which is simple payment verification clients, where you have let's say the wallet in your phone, downloads proofs, verifies everything locally, and then potentially sends transactions to the peer-to-peer network, and everything's trustless and decentralized. That is the world we were promised, and that is the world developers want. But the world developers have is the one on the left here, where you have a mobile phone, you have an application, and then you're talking to a full node infrastructure provider that runs it on your behalf. Now, this is great. It got us going. It gets adoption. But if this is where we're going to be long term, it kind of defeats the whole purpose of having a decentralized network. So in order to formulate this problem, what I was thinking is, who doesn't like a nice equilateral triangle? And that's why we have the RPC trilemma. So what we want from our RPCs is for it to be reliable, performant, and cheap. Reliable really just means all the things that we like from our blockchains: decentralized, trustless, verifiable. Performant is kind of what we get from classical Web 2 scale, Web 2 cloud infrastructure. So you have centralized load balancers, you have elastic scaling, you have DNS, basically what makes centralized node providers very efficient. The last thing we need is for it to be cheap. The application needs for it to be cheap to use. Node runners need it for it to be cheap to operate. And we also need to be efficient in terms of resource consumption, bandwidth, CPU, all that good stuff. This is the RPC trilemma. And why am I here? So what we're doing at Pocket Network is we're building a decentralized RPC protocol, really just trying to decentralize that gateway to the beautiful decentralized world behind it. There's a lot of interesting work that's going on here, but a couple of the really cool things that I'm excited about is things like having on-chain SLA. So we have different protocol level actors, something called the fisherman, for example, that constantly checks for sync checks, does health checks, and verifies how good the servicers that service your RPC calls really are. There's a lot more that's going on behind the scenes, but the reason I'm here is I've already been having a lot of really interesting conversations with people at the conference around light clients, around zero knowledge. I had a 30-minute conversation with polynomial commitments yesterday, and looking a lot into the data availability problems that projects like Celestia are solving. So if someone's from Cello, or if you know a lot about light clients and zero knowledge, please do come. I'd love to resolve the RPC trilemma so we get all three of the best worlds. Okay. My name's Olshansky, Pocket Network.
Thank you very much.
Thank you, everyone. And I'm here representing ARM-DS Lab. The problem we are looking at and trying to solve is a problem actually all the science technology professionals are facing. As you all know, in the US, and every year, there are about more than 300,000 patents issued, right, in the US. And worldwide, the number is even bigger. But how many of these patents get utilized? And according to statistics, usually it's less than 5%. So a lot of these IPs got wasted. And besides this, there are also many inventions and was not able to make it to the patent, right? Because the process is very long, and also the cost, and sometimes complicated to many people. So, and because of this problem, and in last 2 years or so, there's a lot of people trying to utilize Web3 technology, especially NFT, to simplify this process, to help people. So some of them actually mint some NFT, right, and mint some IP and into NFT, but they got lost because now the current NFT market are basically full of arts IPs. Not many people are paying even attention to science IPs there. And the second is that they need some kind of promotion, right? They didn't get. So some kind of writing on this train, and we built a special NFT marketplace for science and technology. So for science technology professionals, they can come to our platform to mint a paper or a pattern or just a set of data or anything, right? Then can mint that into NFT then for exchange. So, and our platform has built up already and start to be utilized by our community. And as you see here, and our platform is based on a few chains, Ethereum and Neo and Avalanche, and also others. Besides that, we also have been utilized other Web2 technologies. So in order to really make this and work for thousands or millions of people, there's many technology challenges we are facing. So we are looking for people to help. And actually for this project, we already got a lot of media attention. So people call us as the world's first NFT marketplace for science and technology. And we also get a lot of emails and requests. So there's a big demand. And then also, as you say, economically, if we can turn It's now like 95% of the IPs only increase the utilization from like 5 to 10, and it's going to have a huge impact. So we welcome everyone to join us, and developers, partners, investors. Thank you.
Thank you. Next up, Sophie with Checkmate.
Hi, I'm Sophie from TU Vienna, and I'm going to very briefly present the main idea of my PhD project, ongoing project. It's called the Checkmate Framework, and it's about the game theoretical security analysis of blockchain protocols. So what we do is on the slide is the main overview of our concept. So we take a protocol. So far we focused on payment channel protocols, which were discussed this morning. We model them as a game. Please don't look at the details of the game. It's just like to see how big it is. We use extensive form games, so trees. This one is the closing game of the Lightning Network, so the closing phase. And what we do with such a game is we have our security properties, which are also defined as formal properties in game theory, and then we put these two together and check if the game satisfies these game theoretical properties. We recently automated that later part. And what security properties do we have? So what game theoretical security properties do we have? We consider honest, rational, and Byzantine users. So the three emojis on top show that. And we want to have two high-level properties. We want to align honest with rational behavior. That is that users should not profit from deviation from the protocol, even if they collude. And second of all, we want to protect honest users against both rational and Byzantine adversaries, such that honest users cannot lose any resources, cannot be harmed, even in the presence of these adversaries. An example of such, where that can be applied is the closing phase of the payment channel. So where it is in fact possible to behave dishonestly, so you can publish an old state, but you might be punished. If you're interested in that work, if you have any concerns, comments, ideas to extend that, check us out at LinkedIn, write me an email, catch me in the coffee breaks. We have the prototype of our automated framework on GitHub, very recently published, and then there is the extended abstract on the automation part, the top QR code, and the game theoretical framework, like the conceptual basis in the paper on the lower QR code.
Thank you very much. Next up, Boson.
Hi everyone, I'm Jonas, and I'm going to tell you a bit more about what we're doing at Boson. So at Boson, we had this idea of enabling a future where all the world's physical assets are listed on a single open system. Not only that, but also can we lower the transaction costs of triangulation, so search essentially, transfer and trade of physical assets, and trust to be near zero. So this is kind of the idea we set onto with our V2 protocol launch. And in kind of researching this, we discovered three core problems to solve to enable this. So the first one is the physical asset oracle problem, which is around representing the state of a physical asset on chain. The second is the fair exchange problem, which is about trust and trust minimization in exchanges online. And the third one is really this idea of how can we create the single digital market for physical things. So this got us to our V2 design. We just submitted this to audit, smart contract audit last week. And what we're launching there is an efficient, optimistic, fair exchange protocol. And we kind of captured all of this in a single design. So what you can see there on the left is the game tree of a boson protocol transaction in the protocol. And bringing it back to the first slide and our goals there, we solve for kind of the discoverability and searchability of offers through having like on-chain offers that sellers create. We lower costs of trading and transferring physical assets through the tokenization of promises as redeemable NFTs. So you can think of these as like tokenized forward contracts to receive physical assets. And then the third is we have an optimistic exchange settlement. So we make an optimistic assumption that buyers will receive the asset, and if they don't, they can raise a dispute, and then we resolve disputes through a combination of game theoretic incentives and escalation to third-party dispute resolvers. Yeah, so if you're interested in that, we have our white paper online. You can check it out under bosonprotocol.io. And yeah, thanks for having me.
Thank you.
Hello everyone, my name is Otto Nagel, and I ask you guys to imagine a moment when you were 13 years old. My moment was really easy to remember. It was the first time I was introduced to blockchain. My mom there, she's a doctor, but she started to learn how to invest. And then she bought Bitcoin in 2015. But some months later, she sold it. I was young, but I remember she telling me how she felt insecure about having her money holding in some private keys, some random words. And this stuck in my mind. And 7 years later, here we are, dealing with the same old problems from 2015 and not getting the non-crypto people into the space and the benefits of blockchain. Nowadays, I'm living here in the Bay Area, but back in Brazil, in my university, Link School of Business, we made a partnership with ArcelorMittal to create a company. Our main goal was to create a new startup with the ArcelorMittal, the biggest steel company in the world. And our goal was to focus in solving the problems of the steel ecosystem with the blockchain technology. So we came to the Bay Area to understand more how Web3 is being developed, and I came with really interesting thoughts. I saw that were many people creating nonsense projects that there were no people using actually, and with no usability, just raise money from funds. But there were actually creating meaningful projects that changed the perspective of blockchain, but almost no projects were focusing on the non-crypto people. And that's our challenge, because we're dealing with a traditional company, ArcelorMittal. And after deep research, we found a huge problem in the budget area, and because there is no place to companies to see in real time the materials price. And this problem has an end date. We're creating a marketplace to show in real time the price to connect the suppliers, such as Arcelor, to the construction companies. Cool idea, but you're probably asking yourself, where is Web3 in it? So imagine all the transactions that nowadays work to banks around the world. Imagine this in our platform with blockchain and made instantly. So that's what we are doing. More than that, we have plans to make everything trackable and to create a whole ecosystem with tokens with that. But before I end my presentation, I would like to leave a final thought for you guys. How do you are addressing the Web3 space for the ones that just won't download MetaMask? If anyone have thoughts on how to deal with blockchain in traditional companies, send me a message. I'll be pleased to talk with you. Thank you.
Thank you very much. Tacticas.
Hello, my name's Aaron Schutze. I'm Research Director with Topple. We're a Layer 1 Nakamoto-style proof-of-stake blockchain. And I'm going to be talking about a project I've been working on called Tacticos. It's a modification to the underlying protocol of Ouroboros Praus. And it introduces a notion of a difficulty curve, and which depends on the slot interval. This is a discrete time interval between slots of a block. So time intervals in these round-based proof-of-stake protocols have discrete time intervals between their blocks. And we define a staking threshold function that has this property of independent aggregation. This property helps us aids the analysis and mitigates this sort of grinding in multiple accounts. And Epoch updates, the private VRF lottery that takes place in a slot-by-slot basis, are all based on the Ouroboros Praus protocol. Now, this leader election mechanism, the kind of intention is to mitigate the, or improve the security properties in terms of the delay of the network. Now, to actually predict what block frequencies we get with a given difficulty curve, the kind of difficulty curve is chosen as a global setup. So we have a freedom to design this difficulty curve as a protocol rule set that everybody agrees on. And this affects the block frequency and changes the security properties of the underlying protocol. And we can predict this block frequency using a stationary distribution in a Markov chain framework. And the Markov chain is kind of shown to the right. It has discrete time intervals. The states are, each state is represented as a discrete time interval. And you get a recurrence time Markov chain that helps us normalize this stationary distribution and make predictions about what the block frequency is. So in this modification, we're designing a difficulty curve that has this characteristic forging window and recovery phase. And what that does is gives a temporary boost to the rate of block production under synchronized parties. And then unsynchronized parties forge at a lower rate of block production in this recovery phase. So the modification introduces a sort of limited form of grinding, but we can see with simulation results that this grinding doesn't give an adversary too much advantage with respect to the block frequency. And the underlying result that we're trying to calculate with this numerical model is a consistency bound. Now, the consistency bound of this system is the threshold that the adversary has to have of the resources in the system. In this case, it's stake. And the we have a numerical result that shows that consistency properties can be improved with respect to network delay. Is that my time? All right. So this consistency bound result is an interesting kind of, we see that it can exceed this proof of work bound that's given by an analysis in another paper. So that's my result. Thanks.
Thank you very much.
All right, hello everyone. Thanks for the opportunity. I'm going to present a recent paper that we have, joint work with Nir, Shemaya. I'm Ding Liu. This is called Cost of Security of Layer 2 Network, Evidence from Polygon Network. So what we have is we know like since late last year, Uniswap starts to support both Layer 1 and Layer 2 liquidity pools. And so now the traders could choose whether they want to do it on Layer 1 or Layer 2. And here is the data for 6 months, what's everyone's trading value. As you can see, what most people do on Polygon is very small value transactions, while on Ethereum are large value transactions. And the question is, why is that? One of the reasons is, the gas fee on Polygon is much less than on Ethereum, but on the other hand, once your trading value gets large, the slippage effect jumps in, right? So what we do is we go ahead and build an economics model, and we are trying to find what's the optimal monetary point for people to start trading on, start switching from Polygon to Ethereum. And we go to the data of millions of transactions to figure out when do people actually switch from trading from Polygon to Ethereum. And here in the graph, what you can see is what the blue line is what empirical we found in the data, when do people switch. And the red line is when do people should switch to maximize their monetary profit. And it turns out there is a very consistent gap between the theoretical prediction and what people actually do. So based on our theoretical model, what we have here is we estimate people's belief on the cost, on the security difference between Polygon and Ethereum. And it's a very constant, it's a very stable belief over the last 6 months from 2021 December to 2022 June. And we estimate that belief to be 1.93%. And it's relatively large and can't be neglected. All right, and feel free to, our paper, it's available on SSRN if you want to read more details about it. We're also going to have UCSB, University of California, Santa Barbara, also have a DeFi seminar that happens every other week for the next year. So thank you.
Thank you very much. next, and the uniqueness weighted voting.
So hi everyone, so I'm Zach from the National University of Singapore, so I'm a visiting researcher at the law faculty, and I'm going to talk about uniqueness weighted voting. So as we all know, DeFi DAOs aspire towards decentralized governance, but the problem is that they have concentrated holding of the governance tokens. So according to the European Central Bank's research, 80% of the total supply of circulation of Uniswap's governance token is concentrated in holders with balances of over 1 million uni, and 1% of the total token holder addresses hold around 97% of the total governance supply, and this is just recently in April 2022. So how do we address this, right? We need to go beyond just quadratic voting. So we have quadratic voting or other forms of novel voting mechanisms that try to allow the minority token holders to have a greater voice in the final vote tally. But the problem with quadratic voting is, firstly, it relies on Sybil resistance. And even if you can address the Sybil resistance problem, the second problem is that it only goes to the level of allowing more individual humans to take part and have a greater voice, but it does not measure the uniqueness of the perspective of each individual user. So it's a bit weird to quote Vitalik since he was just here, but he said that many people seem to agree that an ideal voting mechanism would somehow keep diversity in mind, giving greater weight to projects that are supported not just by the largest number of coins or even humans, but by the largest number of truly distinct perspectives. So how do we measure this uniqueness of each voter? So I propose that one possible approach we can take a step towards is computing a uniqueness score of each voter based on, firstly, the graph of attestations. So we are still in the early stage of soulbound tokens now, but with the soulbound tokens, we can look at the people who issue the soulbound tokens and the transferees of the soulbound tokens to create a graph of the attestations created by soulbound tokens, as well as other potential tokens like your proof of attendance protocol tokens as well. And then combine that with the past voting activity, which is all publicly available for us to compute. So creating a vector representation of each voter using the past voting activity, perhaps doing some dimensionally reduction on that, and then coming to compute a uniqueness score that can be used to adjust the weight of each voter's influence in the final vote tally. So if you're interested in this, I'm happy to chat more, and perhaps we could collaborate on modeling out this. Thank you.
Okay, so a quorum system, like what you see on the left here, is something very useful to have in a distributed system because it allows you to solve problems like consensus despite failures. But one limitation of quorum systems is that you need a pre-existing agreement on what constitutes a quorum. So here you need a pre-existing agreement in this example on the fact that there are 4 nodes and 3 out of 4 is a quorum. Or if you do proof of stake, you need a pre-existing agreement on who has how much money and what's the threshold for a quorum. And this might be a problem in some permissionless settings. So what if, instead, we forget about this requirement and we allow every node in the system to just pick their own quorum, and we don't have agreement on quorums? So that's what you see on the right, and we call that a heterogeneous quorum system. And it seems at first sight that it's going to be chaos, because in this example, there's even quorums that don't intersect at all. But what's very surprising is that actually it's not going to be chaos. Such a system can work. And actually this kind of stuff is used in the Stellar network, for example. And so to show that this can work, we decided to reach for a very powerful yet well-understood mathematical tool called topology. So the idea is to identify the quorums as the open sets of a topological space. And now our quorum system is a topological space, and we can use all the mathematical results that people came up with for more than 100 years now, since those famous mathematicians here established the field of topology. But if you know something about topology, you will say, wait a second, there's a problem here. Because in a topology, we need to satisfy two axioms. The first one is that the union of two open sets must be open. And that's fine, because the union of two quorums is a quorum in a quorum system. But the second axiom is that the intersection of opens is open. And this is a problem, because in a quorum system, the intersection of two quorums, for example, two majorities, is not necessarily a majority. So in fact, we don't have a topology. We have what we call, and this is new, a semi-topology, which is like a topology, but we remove the intersection axiom. And this has some very interesting mathematical ramifications. And strangely, that we know of, it seems that nobody investigated what happens when you remove the intersection axiom. So if you want to see what mathematical structure emerges when you remove these axioms and what we can conclude about quorum systems from this, please check out our paper draft at the address you see here. Thank you.
Hello everyone, my name is Reliance. I'm the CEO co-founder of IoTex. So we have been working on bridging the real world events and insights world in the past 4 years. So we have been like a layer 1 chain down from scratch, EVM compatible POS chain, so which has been launched in 2019 and actually have like a 300-ish, applications already run on top of. So today, roughly talking about like a new infra project we're working on, basically address the real needs and asks from Web3 developers. So the challenges here, like the developers always come us to see, is I have a bunch of devices, could be like a wearable, bike, scooter, or solar panels in my home, right? How could I actually hook up this one with a smart contract and even some token economics so I can turn them into some sort of mining machines? Basically monetize like a real world data, real world utility. If there's such a an infrastructure can help me to shorten my cycle for the development. So that's why we're building this web stream, so definitely address the needs. So at a very high level, how it works is actually it's like a decentralized infrastructure, basically getting a lot of data stream from different devices. Could be your wearables, could be your rings, could be your bike, scooter, everything. The data stream itself is actually have some sort of DID auth and also end-to-end encryption. So that actually ensures the privacy for the user. When the data actually coming to the infrastructure, so the infrastructure will unopen the data and also trying to do some computations according to some specific logics the user actually puts into the WAS runtime to actually compute some sort of proof. And finally, the proof will become something, going to the smart contract, basically says, oh, I'm running 6 miles every day, or I'm driving very safely, or I have slept well, so I can get some sort of tokens, right? So this is at a very high level how everything works. So we are working with a few teams, doing some very pioneering stuff. Actually, some is called sleep to earn, so you can hook up your wearables, all the way up to a smart contract and sleep more to earn some sort of token. And we're working with Mobi, basically to do some sort of a trusted trip test drive. So they're having some hardware put into the car and letting people drive around, and also all the data gets compressed, validated, and also produce a proof that goes to a smart contract. And finally, some sort of fractional ownership. So this stuff is really new. So there's no such infrastructure in the Web3 space so far. So we are the first one, kind of trying it out. If you are interested in terms of you're a developer or you are infra guy, feel free to just talk with us or maybe send us an email. Thank you so much.
I remember when a Norwegian architect was asked why he moved to Brazil to start his own business. He said, here, there's a lot to build. There is already made. It means that in Brazil we have many problems to be solved. In other words, we have many opportunities and a huge market, more than 200 million people. I'm Angelo, an entrepreneur from Brazil. Precisely 2 years ago, we started Link School of Business. The first university focused 100% in entrepreneurship in Brazil. This means that every student who is admitted needs to want to create their own business. It's the Disneyland for entrepreneurs, the paradise for investors. In addition to all other areas, we are creating a Web3 ecosystem. We have the Link coin, our crypto token on Polygon. We have Link Auction, our auction platform on Polygon, where you can bid using Link coins to get access to our community events, products, and experience. We have Link plus ArcelorMittal, a partnership between us and the biggest steel company in the world, created to solve problems in the steel chain using Web3 and Metaverse concepts. We have MA5, our university's business accelerator, where we facilitate startup funding, mentoring, and everything you need to create and scale your idea. We have the Lodge, our campuses besides our headquarters in São Paulo. We already have one here, side by side with Stanford at Atherton, and one in Berlin, Germany. Furthermore, we are opening other ones in every place that has an innovation ecosystem around the world. This is the QR code for the Link Coin Club on Discord. If you have a project, if you want investment, if you want to invest, if you want to learn, if you want to teach, if you want to create, or if you want help in creating, you are more than welcome. Just like we love to say to the new members of our community at Link, welcome. Welcome home. Thank you so much for your time, guys.
Thank you.
Hi folks, thanks a ton for sticking around. I'll keep it short and sweet. My name is Yuri, I'm with Puma Browser. How many of you have used Puma Browser or have heard about it? Could you raise your hand? Okay, small audience, okay, cool. Pretty simple, we're a mobile Web3 browser. We've been quietly building for the last 3 years. We recently crossed 500,000 downloads, which is a very important milestone for us. And we started with a very simple idea. Let's build a private browser that has you as a customer and not as advertisers. And let's use this cool new micropayments technology with an interoperable protocol called Interledger to facilitate that. If you want to catch up on Interledger, Dan Robinson actually gave a talk here in 2019 called Why HTLCs Are Considered Harmful. And since then, he became a celebrity. Interledger, on the other hand, is not necessarily the most popular protocol, but we think, given the recent changes in the regulation and other things, might be the last man standing, so we'll see how that plays out. Since then, we've added support for IPFS, ENS, Handshake, and a bunch of other things. And yeah, you can use it on your iOS and Android phone. And the thing I wanted to highlight today is a set of open problems. We're a very small team. We're very excited to work with the community on two things. One, we believe that feedback is a gift, and we'd love to know what you'd like to be added next in Puma Browser. Feel free to tweet at us or hit me up on Telegram. I'm HTML5Ket, or we are Puma Browser on Twitter. And then the second one is a much more complicated one, which is we're working on designing the incentive structure to support three things. One is the sustainable and long-term growth and development of the project. We've seen a lot of browsers come and go. Most of them are funded by Google one way or the other. Most money to Google comes from ads. So this is not necessarily a very good long-term sustainable business model, and we'd like to change that. Two, we'd like to encourage discovery and usage of new dApps and protocol. We think there's a lot of exciting things happening in crypto. I come from math background and some deep tech stuff, and I've seen a lot of technology die for lack of adoption. So we think it's really important to make it easy to use and discover it on your mobile phone. And three, we think there's a much better way to monetize your content and your apps as content creators and developers, and we'd like to support that as well. Thank you very much, and I'm around here. If you've used Puma before, I'm happy to give you a limited edition sticker. Thank you so much.
So, hi everyone, my name is Camila, and I'm on the stage to present this new exciting project, Babylon. But first I want to talk about the old project, about Bitcoin. So, Bitcoin is one of the most secure blockchains in the world, but it is supported by this tremendous hash power that results in overwhelming energy consumption, which is now compared to energy consumption of some other countries. And the main utility that we see in Bitcoin right now is just a store of value. So all this work done by miners is used just to sustain this store of value system, and this seems like an overkill. But I really doubt that we can ask miners to just stop mining. So the right question to ask is there any other utility in Bitcoin? Is there anything else we can use Bitcoin for? For example, it's security, because as I said earlier, Bitcoin is one of the most secure blockchains. And luckily, yes, we can do that. We can share Bitcoin security. So we can use Bitcoin to support newer and smaller chains. So these other chains, they can communicate with Bitcoin, and in return, they can get some additional security guarantees. But if all chains start doing so, we have a risk of congesting the Bitcoin network, and this is just not scalable. So to address this issue, we present Babylon. So Babylon does this communication on behalf of the other chains in a trust-minimizing manner. So Babylon does not become a single point of failure, but in return, it provides this Bitcoin security. So you can think of Babylon as a conduit of Bitcoin security. It borrows security from Bitcoin and shares it with the other chains. So of course, this is all oversimplified, so I encourage you to scan this QR code and take a look at our website. We have a blog post explaining our technology, and we also have explanations on some of the benefits you can get from using Babylon. For example, proof-of-stake chains, they can reduce their unstaking period from few weeks to just few hours, which I think is pretty exciting. This is our amazing team. It's scattered all around the world, but our research team is located here at Stanford. So if you see any of these people here and you have some questions or comments, please let's have a chat. But to be fair, you'll probably only see 5 people out of this team, mostly from the research team, is Professor David Che, Professor Sriram Kannan, me, Dionysus, and Nusret. Yeah, if you're a founder of a chain and you're looking for ways to enhance your security, to provide additional security guarantees, let's also have a chat. Thank you.
Thank you.
So Ethereum is very expensive. There's no way to make high-scale apps right now. Probably the best solution you've thought of is, let me go to a layer 2. The problem with every shared layer 2 is that you're bidding against all these other really popular apps. So it's kind of like if you were to put an app on an AWS server, you're like bidding against Facebook, Uber, Apple, all these companies to have your app have block space on the blockchain. So any high-scale app has basically decided, let's build an independent chain, but that has 2 main problems. One problem is that a lot of them are not EVM compatible, and the other main problem is that they're not sharing security with Ethereum, so it's like not using Ethereum's consensus. So now it's possible with ZK EVMs that you can create your own app chain, and this app chain is going to have the security level of Ethereum, and you actually get the scale of having your own chain. So you kind of get the best of both worlds. And so your users for your app can basically send transactions to this chain. We use like a zero-knowledge roll-up to basically verify that the transactions happen correctly, and then we roll that up to Ethereum. And so each of these chains can have like 2,000 plus TPS. This is like the horizontal scaling feature, roll-up-centric vision that Ethereum's moving towards. So I think we're at this really exciting time in history right now where it's kind of like when AWS came out for the internet, where app developers can basically very easily get compute as a service. So if you want to build Uber, Instagram, or Snapchat, something like that, you could write your app, use AWS, and basically scale to millions of users. And so we think the same thing's now happening with ZK EVM app chains. So basically, you're going to be able to quickly create your own chain and then write your smart contracts and then scale to millions of users. And so it's going to unlock use cases for a lot of like games, metaverses, social apps. Like if you want to build a decentralized Twitter, decentralized Uber, if you want to build a game that has millions of users, this is kind of like the path forward. And so we got really excited about this vision for the future. We're building this with Atlas. If you're excited about this, if you want to build an app that can actually support millions of users on the blockchain and have Ethereum level security, then come check us out, talk to me, atlaszk.com.
Thank you.
Hello, everyone. This is Paraspace. We are a DeFi protocol launching soon on Ethereum blockchain. It's a generic DeFi, generic and scalable DeFi protocol. So we will walk you through a demo. Can we click on the product demo, or no, it's not possible? Okay, it's not possible. All right, then I guess. All right, yeah. So basically, what we're providing is so it's a generic DeFi protocol where you can provide multiple set of assets such as NFTs and ERC20s and as collateral, and you can take loans against them. Yeah, and so basically, in order to enable NFT to be NFT financialization, we know that the calculation of NFT pricing is pretty, tricky. So we have done research on price calculation, and so we have basically measured different TWAP calculations at different periods, and we have measured the reactiveness of this TWAP calculation, and to see basically to eliminate some of the like out of bound like values, so like some of the extreme values and the fluctuation that could happen momentarily in the prices, and so in order to come up with the best pricing mechanism. And so this is an example of Doodle. We did this study on Doodle to basically eliminate the loss that could occur to the protocol. And you can share maybe in the next slide.
Yeah, so the next one is a collection-wide sort of risk analysis over how reliable it is to add a specific collateral to support, right? So what really matters in the end is that a tailwind event, which is, let's say, 5% of chance, a specific NFT collections, what is the probability that it have to sell below the floor, right? That what is really what matters, because we're pricing the whole NFT as the floor collection with the TWAP price. So if you look at it, sort of the value at risk, especially we come up with the concept of the conditional value at risk, we're only looking at that, tailwind events, and what is the percentage, what is the average loss given that, like at 10% of chance or 5% of chance that you have to sell below the floor based on all the historical data. And then with those parameters, we can determine what would be the appropriate loan to value ratio, and then the appropriate sort of liquidation threshold and all that in order to support a new type of collection. Super quantitative driven data, but once there are more sort of like, on-time liquidity through liquidity pools such as NFTX or SudoSwap, then this can also be on top.
Okay.
Yes.
Can you guys wrap up?
Yeah. So we're pretty much supporting a wide range of NFT collections, but one of the very unusual ones is Uniswap V3, and so we've done also research on that. We don't have the time to show this, but thank you so much. We are launching soon, and here's our contact if you want to contact Hugo. All right, thank you.
Thank you.
Hi, I'm from Roro, a decentralized search company. We are developing a decentralized search engine. As you know, search engines are distributed by their nature, so operations like crawling the web, constructing the index, and computing the rank are inherently distributed, but now the question is, can we decentralize that? Because now, as you know, search business is conducted by these giant corporations that hoard the data and essentially make money out of users. So we developed an architecture backed by a system of ledgers that allows us to record the transactions, the operations that are necessary to perform web search. And our architecture allows us to do distributed computation of rank and a guaranteed cryptographically secure delivery of this ranked pages, ranked lists to users. Advertisement, so the revenue model comes from the advertisement, and the advertisement revenue is distributed among the nodes participating in the network. Our native coin is called Knowledge Coin because we draw parallel with crypto mining. We have, in analogy, we have knowledge mining. And eventually we want to go to things like knowledge graph construction at the planetary scale and transform web as it is to actual knowledge system, eventually to open data vaults that are stored in centralized companies like IBM, Raytheon, and so forth. Yeah, that's it. Thank you.
Thank you. Now we have a couple talks without slides.
Thanks, Benedict. Hello and good afternoon. Lightning struck and my slide didn't quite make it to Benedict in time, but my name is Subra. I'm with Stanford in Cyber Knowledge. And I just wanted to say that we're working on some exciting projects that relate to next generation identity, Web3, verifiable credentials, and distributed key management, and also privacy and cybersecurity that uses or that has applications of zero-knowledge proofs, and also some graph and machine learning. So if you're interested in any of these topics, either as a contributor or an investor, please reach out to me. I'd love to talk to you. Again, this is a memory test, so my contact information, I'm the guy in blue shirt. I should be around. And psubra@ieee.org is my email if you want to reach me. So again, I'll repeat that. P as in Paul, subra@ieee.org. Thanks a lot. Thanks.
Thank you very much. Okay, I think, do you want to, one final talk, last but not least. And then.
Good morning, I'm Pavan. And other interesting facts, I lead SunWest. It's a 42-year-old financial institution, and we've developed a one-of-a-kind blockchain technology to increase housing and affordability and accessibility. The real estate business has been hesitant to embrace new technologies. Why? Because of 6% fees to real estate brokerages, 3% fees to lenders. And what that means is in Palo Alto, a $1 million house, you pay $90,000 in fees. And in Palo Alto, you can't even buy an outhouse for $1 million. So in a $2 trillion mortgage market, that's $180 billion is wasted on fees. We've been leading the charge to change that. We've hired hundreds of software engineers and have inspired our people to embrace people-powered technology. Our platform uses distributed ledger technology, AI, to completely change the mortgage process. We've done this from San Juan, Puerto Rico. Our engineers are driven by their personal experiences to bring equality and wealth creation. Since necessity is the mother of invention, economics drives innovation and scientific expansion. Up until now, the study of application of distributed ledger technologies has been a solution looking for a problem. Satoshi proposed the solution to the double spending problem. So we created virtual ledgers with virtual tokens and virtual value assigned to it. The time has come. My team has implemented NFTs, blockchain to solve real problems of high transaction fees and financial accessibility to real estate and real money. We have demonstrated that NFTs and blockchains can change how real estate is exchanged and be used to prove ownership over any asset. Real estate is over $2 trillion annual market with no central clearing authority. It's brilliantly fragmented, distributed, decentralized. Real estate is ripe for distributed ledger technology. Our platform, Morgan, uses AI to completely change the real estate and mortgage process. She governs our blockchains. Problems in a real estate transactions that Morgan AI solves are, you don't need to rely on trust. The buyer, the realtor, the seller, the loan officer can rely on the blockchain and to give them transparency and security thanks to Satoshi. You will know the money is there, financing is in place, secure, source of funding, timeline, and history. Communications, number 2. No need for endless email chains or unanswered phone calls. Finally, costs. Fewer linear processes, fewer people involved means fair lending and technology and the elimination of unconscious bias. Embracing blockchain and our people-powered technology, we have stripped out bureaucracy in the lending process, in the housing markets, and eliminated redundant steps. We are a financial enablement company. As we move forward, we will use blockchain and crypto to bring proven trading standards to the real estate industry, not tomorrow, but now. So if you're interested in making a real difference, see me, I'm here.
Thank you.
Let's do it.
Okay. Let's give one big round of applause to all of the speakers again. Thanks for everybody who gave the talk. And yeah, I think we have a little bit break until 2, and then I think we continue with the next session. I really hope that next year we'll have at least one song or something, maybe, in the lightning session. It's all allowed. But yeah, thank you very much.